All right. Can we start, Mas Robi?
Robi or Mas Hamid, can we start? And how about the YouTube channel? Yes.
We'll start shortly, Prof. Okay, good. We start, Prof. Adila, please.
Okay. Good morning, everybody.
Good morning.
Thank you. Right. So, Honored Rector of Universitas Indonesia, Professor Dr. Ari Kuncoro, Acting Dean of the Faculty of Computer Science, Universitas Indonesia, Dr. Petrus Mursanto, Rector of Defense University, Indonesia National Armed Forces Vice Admiral Dr. Amarullah Octavian, Director of Cyber and Cryptography, National Polytechnic, Cristianto Noviantoro, Mr. Cristianto Noviantoro, Honored Acting Dean, honored speakers, our plenary speakers today already present here in the opening event. IEEE President Professor Toshio Fukuda, IEEE Vice President and Chair of Member Geographic Activities Board, Professor Kuk Jin Chun, Director of IEEE Region 10, Professor Akinori Nishihara, IEEE Region 10 Director-elect, Professor Lance Fung, Head of Agency and Technology Assessment and Applications of Indonesia, Dr. Hamam Riza, Chairman of the National Association of Higher Education in Informatics and Computing, Professor Zainal Hasibuan, Professor Yves Lepage from Waseda University, fellow organizers, friends, colleagues, participants of ICACSIS 2020 and IWBIS 2020. Once again, good morning. I hope everyone is doing well in the middle of pandemic, but we are very excited. Today, we will have the opening event of ICACSIS 2020 and IWBIS 2020. So let me first welcome everyone to the 12th International Conference on Advanced Computer Science and Information Systems, or ICACSIS 2020, and the 5th International Workshop on Big Data and Information Security, or IWBIS 2020. ICACSIS and IWBIS are two annual conferences hosted by the Faculty of Computer Science, Universitas Indonesia, fully supported by the university, and sponsored by IEEE through IEEE Indonesia section. Additionally, this year, we are very happy that Indonesia's Defense University is acting as the co-host of ICACSIS, and the Cyber and Cryptography National Polytechnic is acting as the co-host of IWBIS. ICACSIS topics encompass a broad areas in both computer science and information systems. Meanwhile, IWBIS is more focused on topics on big data and information security. Both conferences this year are held at the same time in the same location, and both are fully international conferences and gather researchers and practitioners from many places around the world to report on the latest advances in theory and applications on the broad areas covered by both. Specifically, ICACSIS this year received 142 submissions, and from them, we accept 73 papers from 14 countries. Meanwhile, IWBIS received 49 submissions and accepts 23 papers from 10 countries. This year, due to pandemic situation, both conferences have to go virtual. Nevertheless, we hope that it doesn't diminish the value and experience of both conferences for all of the participants. Before I start, let me thank all the organizers, fellow organizers, student volunteers and everyone who helped organizing these conferences. So, ladies and gentlemen, to start the opening event, let us hear the national anthem of Republic of Indonesia.
Darahku, di sanalah aku berdiri, jadi pandu hidupku. Indonesia kebangsaanku, bangsa dan tanah airku. Marilah
Kita bersatu,
Indonesia bersatu.
Hidup negeriku, bangsaku,
Raku
semuanya.
bangunlah jiwanya, bangunlah badannya untuk Indonesia Raya. Negeriku yang suci, Indonesia Raya, Merdeka Raya, yang suci,
Thank you. Thank you. Ladies and gentlemen, today marks the second day, actually, of the planned 2 days of ICACSIS 2020 and IWBIS 2020. Already yesterday, from early morning to evening, we have heard and seen presentations from more than 100 papers on both conferences on various topics. And in addition, at the end of the first day last night, we heard and seen a presentation, plenary speech from Professor Anil Jain from Michigan State University. So from these presentations and accompanying discussion, we hope that all participants gain a lot of fresh ideas, received novel insights, and uncovered new direction for future research and collaborations. Now, for the second day, starting with this opening event, we will have an array of speeches, plenary speeches from Professor Toshio Fukuda, Professor Kook Jin Chun, and Professor Akinori Nishihara, and later followed by keynote speeches of ICACSIS and IWBIS. Some of the speakers are here already. So let us hope that today's event runs smoothly and brings good to everyone attending or participating in these conferences. So next, to continue, let us call the Acting Dean of the Faculty of Computer Science, Universitas Indonesia, Dr. Petrus Mursanto, who represents the host of both conferences, to give his opening remarks. Dr. Petrus Mursanto, the time is yours.
Thank you, Pak Adila. Is my voice clear?
Yes.
Ya. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, Ibu Bapak yang saya hormati. Good morning, ladies and gentlemen, all our respected guests, participants, and presenters, our distinguished speakers. Praise to the Lord, the Almighty, who let us meet together through this online media this morning. It is a great pleasure for me to welcome you to the 12th ICACSIS, the International Conference on Advanced Computer Science and Information Systems, and the 5th IWBIS, the International Workshop on Big Data and Information Security. We have been organizing these two conferences regularly as part of a series of events in our Dies Natalis Faculty of Computer Science, Universitas Indonesia, in which celebrates the 34th this year. We are glad to know that the participants of both conferences are increasing from time to time, showing the great interest and enthusiasm among the academics, researchers, practitioners, and also industrial community. We perceive that during this pandemic outbreak, which makes us unable to face each other, there still shows a great passion to share knowledge and experience. Even by doing these events online, we reach a wider audience with even more practical and more economical. By seeing this, it reflects that the ICT has an important role in many ways in our life, in which we have increasing demands to be able to provide solutions for various needs. From the papers presented and also today's keynote speech, we come to realize how the implementation of ICT is in various sectors, from meeting personal needs to serving teams or organizations, from education sectors, tourism, finance, and many other sectors. We also notice the current topics related to the roles of ICT in our efforts to overcome widespread of COVID-19. We will still continue to work on the benefits of the ICT for possible future solutions in our life. We do hope that this online meeting has the same intensity to interact one another through lots of discussion, sharing thoughts on the research topics presentations, as well as to build networking amongst the researchers and practitioners, which creates positive collaboration for professional participants and also for the institutions involved. We would like to express our heartfelt gratitude to all of you, everyone present here, and particularly for speakers, papers presenters, and the committee who sincerely dedicated to this event to make it a success. Special thanks are due to our organizing partner, the IEEE Indonesian section, who technically support these conferences with their expertise and skills. Especially, I would like to thank to the following keynote speakers: Professor Toshio Fukuda, the IEEE President from Beijing Institute of Technology and Meiji University. Thank you for your presence today. My pleasure to welcome Professor Kook Jin Chun, the IEEE MGA Vice President from Seoul National University, and Professor Akinori Nishihara, the Director of IEEE Region 10 from Tokyo Institute of Technology, Professor Anil Jain from Michigan State University, who had presented keynote speech last night, Bapak Hamam Risa, the head of Agency for the Assessment and Application of Technology, BPPT, Vice Admiral Indonesian National Armed Forces, Dr. Amarullah Octavian, Rector of Defense University, Professor Lance Chun Chifung from Murdoch University, Australia, Professor Yves Lepage from Waseda University, whom I noticed your dedicated presence in this conference for the last 3 years. Thank you. Professor Jainal Arifin Hasibuan, Chairman of the Apticom from Dian Nuswantoro University, Bapak Beno Kunto Pradekso, Chief Executive Officer of Solusi 247 and Labs 247, Profesor Wisnu Chatmiko, the IEEE Indonesia Section Chair from Universitas Indonesia, and Mr. Hendrik Skibe from Riken Center for Brain Science, Japan. My sincere thank you to all. In addition to those I have mentioned, I also want to call on our institution partners, Universitas Pertahanan as co-host of the ICACSIS and National Cyber and Cryptography Polytechnic, Polytechnic Cyber, dan Sandi Negara as the co-host of the IWBIS. These conferences would have been impossible without the support of each and everyone present here. Thank you all for making this truly great international conference. We ensure the conferences will be profitable and fruitful for all of you. Enjoy the conference. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Mursanto, for the opening remarks. Now to continue, let us hear the opening remarks by Rector of Universitas Indonesia, Professor Dr. Ari Kunchoro.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning for you all. On behalf of Universitas Indonesia, I would like to extend our warmest welcome to all participants of the 12th International Conference on Advanced Computer Science 2020 and the 5th International Workshop on Big Data and Information Security 2020. It is an honor to welcome you all to these two co-located virtual events in the midst of pandemic situation. Universitas Indonesia has a strong focus on research and envisions herself to become one of the top referral higher education institutions in Asia. The university promotes multidisciplinary research involving collaborations across different areas of research. The Faculty of Computer Science is an important part of the UI who pioneer education, research, and community services in the broad area of the computer science and information system. With the world inevitably entering the information age and the fourth industrial revolution, expertise gained through the advanced research in computer science and information technology is critical. Through the faculty, UI hopes to significantly contribute to the prosperity of the nation by impactful work in the faculty core subject areas. Organizing a conference is a means of expanding and strengthening the network of collaboration with existing and new partners from academic community and industry. Exchange of ideas through conference activity can spur the development of new frontier of the research. Moreover, such events offer opportunity for researchers and students alike to obtain valuable feedback from fellow researchers and members of scientific community on the work they are doing and presenting at the conference. Along the above line of thinking, UI applaud the effort of the Faculty of Computer Science to organize ICACSIS and IWBIS now in their 12th and 5th year. Respectively, this demonstrates the commitment of the faculty to the advancing research through strong research collaboration internationally. In the midst of challenging pandemic situation worldwide, we are honored that this year ICACSIS and IWBIS are able to host several distinguished speakers from world-leading researchers and luminaries. The list includes Professor Toshio Fukuda, Professor Anil Jain, AAS and SPIE, computer scientists with the highest age index in the world, Professor Kuk Jing Chun, Vice President of IEEE, Chair of the Member and Geographic Activities Board, and Professor Akinori Nishihara, Director of IEEE Region 10 Asia Pacific. In addition to them, ICACSIS and IWBIS also host a list of distinguished speakers that surely can provide valuable insight and inspiration to all participants of both conferences. I would like to express my sincere gratitude to the distinguished invited speaker for their presence and contribution to the conference. I also thank all of the program committee members for their efforts in ensuring a rigorous review process to select high-quality paper. I would like also to mention the support of the IEEE Indonesia section, National Defense University, and National Cyber and Cryptography Polytechnic for their generous support that enable this event to go ahead in this challenging time. Finally, I sincerely hope that all the participants will benefit from the technical contents of both these conferences. Furthermore, despite the virtual setting, I sincerely hope through the both conferences some fruitful and hopefully long-lasting collaboration can be established and all participants can return from both conferences enriched and inspired to do more impactful work to the society. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Ari Kuncoro, for the opening remarks. ICACSIS and IWBIS 2020 will not have happened without the support of Universitas Indonesia. It is to our pleasure that both conferences remain fully supported by the university. Ladies and gentlemen, this year, ICACSIS 2020 is grateful that the Indonesia's Defense University, or UNHAN, is acting as the co-host. So let us welcome the Rector of Defense University, Vice Admiral Dr. Amarullah Octavian, to give his opening remarks. Vice Admiral Octavian, the time is yours.
Thank you, Mr. Adila. Professor Ari Kuncoro, Honorable Professor Ari Kuncoro, the Rector of University of Indonesia, Dr. Petrus Mursanto, Acting Dean of the Faculty of the Computer Science, University of Indonesia, IWBIS co-host, Mr. Kristianto Noviantoro, the Director of Cyber and Cryptographic Polytechnic, Honorable Plenary Speaker, Professor Toshio Fukuda, Professor Kunjin Chun, Professor Akinori Nishihara, and Professor Anil Kijain. Honorable ICACSIS and IWBIS keynote speaker, Professor Yves Lipets, Professor Lance Chun Chi Fung, Dr. Hendrik Skibi, Professor Wisnu Jatmiko, Dr. Hamam Riza, Professor Zainal Arifin Hasibuan, and Mr. Beno Pradekso, and member of program and organizing committee of ICACSIS and IWBIS General Chair. All distinguished guests, colleague, researcher, professional, ladies and gentlemen, good morning, a prosperous, warm, and spirited greeting. I am the Rector of Indonesia Defense University, Vice Admiral Amarullah Octavian from the Indonesian Navy. First of all, I would like to say thank you to University of Indonesia for the opportunity given to the Indonesia Defense University to participate on these two international academic fora, both the 12th International Conference on Advanced Computer Science and Information System and the 5th International Workshop on Big Data and Information Security. I would like to congratulate the Faculty of Computer Science, University of Indonesia, which are leading scientific conferences in the field of computer science, information system, and information security, which brought together scientists, researchers, professionals, and experts from Indonesia and abroad. Ladies and gentlemen, this year, Indonesia Defense University get the opportunity to have the conference as a co-host. Indonesia Defense University, established since 2009, and has 4 faculties of bachelor degree, 4 faculties of master degree, and 1 program of doctoral degree. Under Faculty of Military Engineering, we have study program of Information and Computer Technology, and under Faculty of Defense Technology, we have 4 study programs, which are Defense Industry, weaponry technology, sensing technology, and momentum technology. All those 5 studies programs in Defense University are very connected with this event. Indonesia Defense University is the melting pot for the professional soldiers with academics in Indonesia. Indonesia Defense University is also a concrete form of military and civilian cooperation in the field of knowledge and technology. IDU students come from the military, civil servants, and best students from all over Indonesia. Indonesia Defense University also accepts several students from many countries. Indonesia Defense University collaborates with various universities at home and abroad, including with military educational institutions at the same level, including Army College, Naval College, and Air Force College. We invite regularly international professors and scientists as the guest lecturer and hope some professor in this conference would come to IDU next. Indonesia Defense University used a lot of effort to conduct some simulation to analyze policy and strategy to formulate priorities and agendas in the field of defense and public policy. We must ensure the next policy and strategy in line with national interests and international agenda. IDU research results were primarily contributed to the Ministry of Defense in Indonesian Armed Forces headquarters. Since 2017, ladies and gentlemen, IDU conducted Indonesia International Defense Science Seminar with 2 concentration plenary on defense studies and defense technologies. We invite also international speakers to bring the bright idea and innovation in the defense area. Due to the pandemic situation, IDU preferred to join the University of Indonesia in conducting these 2 fora. It is a great honor for Indonesia Defense University as a co-host, which is well known as International Barometer of Computer Science and Information System Scientists. As international level conference, ICACSIS and IWBIS become a forum for IDU to share knowledge, experiences, innovation, and the latest scientific development regarding methodologies, theories, and application in the field of computer science and information system and defense technologies especially. The professor and student from Indonesia Defense University are very happy to participate and gain experience in hosting the conferences. We are also very happy to present some of the research and get acquaintance with professor in computer science. Indonesia Defense University believes the result of this conference will be our theme and topic for next research and discussion. Ladies and gentlemen, once again, we would like to express our gratitude to Faculty of Computer Science, University of Indonesia, as a main host of these conferences. We do hope this collaboration may open the next opportunity, such as research collaboration, enhancing academic reputation, joint conference, and share more knowledge together. I thank you.
Thank you. Thank you, Vice Admiral Octavian, for the opening speech. Now, also this year, ladies and gentlemen, IWBIS 2020 is very pleased that the National Cyber and Cryptography Polytechnic, or PSSN, Polytechnic Cyber and Sandi Negara, is acting as the co-host. So for representing PSSN, let us welcome the Director of Cyber and Cryptographic National Polytechnic, Mr. Kristianto Noviantoro. The time is yours.
Thank you very much. Honorable Professor Ari Kunchoro, Honorable Dr. Petrus Murusanto, Honorable Laksamana Madya TNI Dr. Amarullah Octavian, Honorable all plenary speakers, Honorable all keynote speakers, Honorable Prof. Wisnu Jatmiko, member of programs and organizing committee of ICACSIS and IWBIS 2020, and all distinguished guests, colleagues, researchers, professional, ladies and gentlemen. Good morning. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. On behalf of State Polytechnic of Cyber and Cryptography, it is a great pleasure to welcome you all at the 5th International Workshop on Big Data and Information Security 2020. This is a 2 days workshop contain parallel and plenary session. I would like to express my gratitude and a warm welcoming to all speakers, as well as the presenters, and of course, all participants, especially those from overseas. Also, we would like to express our thanks to the Faculty of Computer Science, University of Indonesia, for involving us as a co-host in organizing this workshop. Hopefully, this will be a good start for further joint work in the future. It is no doubt that this century has brought and inspired significant changes in the field of human life, where all people in the world are connected through the internet. IoT technology become a basic platform for almost business processes that gives a lot of benefit for human being. On the other hand, the easiness in connecting any devices in variety platforms unfortunately leaves some vulnerabilities that can be manipulated by some unauthorized people for their own advantage. One thing to be sure, as a product of new life, is a huge number of data that spread widely through the network, which are needed to be well organized to reduce the negative impact and severe damage that is potentially caused by malicious attack. Big data and information security becomes important to be excavated in order to produce the best solution for any potential problem. This workshop is highly dedicated to deliver all possible solutions from the researchers. At the end, we are highly appreciative for all participants who attend this workshop and share their research. I also thank to program committees, organizing committees, and everyone else who contribute for making this workshop delivered. Ladies and gentlemen, finally, please enjoy the plenary session today, and it will be a great pleasure to meet you again at the next event in 2021. Have a nice day. Thank you very much.
Thank you, Mr. Cristianto Noviantoro, for the opening remarks. I hope we continue our collaborations in the future, both the National Defense University and the State Polytechnic Cyber and Cryptography. Right now, so before we start with the main event of today, let us just watch one performance. This time, the performance is from Uluwatu Orchestra. This Uluwatu Orchestra is an orchestra formed by students and staff members at the Faculty of Computer Science, Universitas Indonesia. And this time, the orchestra will perform online, of course, the song Indonesia Jaya. Uluwatu Orchestra, please.
Hari-hari terus berlalu, tiada pernah berhenti. Seribu rintang jalan berliku bukanlah suatu penghalang. Hadapilah segala tantangan, mohon petunjuk yang kuasa. Ciptakanlah kerukunan bangsa, kobarkanlah dalam dada semangat jiwa Pancasila. Hidup tiada mungkin tanpa perjuangan, tanpa pengorbanan. Mulia adanya, berpeganglah tangan, satu dalam cita demi masa depan Indonesia Jaya. Hari-hari terus berlalu, tiada pernah berhenti. Seribu rintang jalan berliku bukanlah suatu penghalang. Hadapilah segala tantangan, mohon petunjuk yang kuasa. Ciptakanlah kerukunan bangsa, kobarkanlah dalam dada semangat jiwa Pancasila. Hidup tiada mungkin tanpa perjuangan, tanpa pengorbanan. Mulia adanya, berpeganglah tangan, satu dalam cita demi masa depan Indonesia Jaya. Hidup tiada mungkin tanpa perjuangan, tanpa pengorbanan. Mulia adanya, berpeganglah tangan, satu dalam cita demi masa depan Indonesia Jaya. Hidup tiada mungkin tanpa perjuangan, tanpa pengorbanan. Mulia adanya, berpeganglah tangan, satu dalam cita demi masa depan Indonesia Jaya. Demi masa depan Indonesia Jaya.
Thank you. Virtual applause to Uluwatu. All right. So before we start, I think let us do another photo session if the panelists don't mind. Mas Robin.
Also welcome Dr. Henry Skype.
Welcome Dr. Hendrik Skibe for we have the opening events, but so let's just do the photo session.
Okay, please everyone switch on again the camera if possible. We have some. Pak Ucok,
Prof. Zainal Hasibuan.
Prof. Zainal Hasibuan, could you turn on the camera? Dr.
Dr.
Sidi Azid,
Dr. Henry,
Dr.
Dr.
Rizky,
Hamam. Dr. Stili Yazid. Okay, maybe we go through. Right. Okay, I will count to until 3 for the photo group session. The last sentence I will say IEEE, so maybe you you will follow them. Okay, 1, 2, 3, IEEE.
IEEE.
Okay, once again, 1, 2, 3, IEEE.
IEEE.
Okay, nice.
Okay, great. Thank you, Mas Robbie, for helping us with the photo session. Right, ladies and gentlemen, that ends the opening events. In a couple of minutes, we will start with the main course of today's event. But before that, let me just read out the schedule for today. So right after this event, right at 9:30, so roughly 9 minutes from now, we will hear the plenary speech from IEEE President, Professor Toshio Fukuda. And after that, we will have the second plenary speech from the IEEE Vice President, Professor Kook Jin Chun. And then we followed with a break, lunch break. And at 1 p.m. Indonesia Jakarta time, we will have Professor Akinori Nishihara, the IEEE Region 10 Director, to give his plenary speech for both ICACSIS and IWBIS. Now after that, the attendees will be split into two parallel rooms for two parallel keynote speech sessions. For ICACSIS, we have 4 speakers starting from 2:30 p.m. until evening. They are Professor Yves Lepage from Waseda University, and then Dr. Hendrik Skibe from RIKEN, Brain Science, and then Professor Lance Fung from Murdoch University. And then we have Professor Vishnu Jatmiko, IEEE Indonesia Section Chair at the last. Meanwhile, for IWBIS, we will have 4 keynote speakers. We start with the head of BPPT, Dr. Hamam Riza, and then Director of Indonesia's Defense University, Vice Admiral Dr. Amarul Octavian, and then followed by wait a second.
Prof. Lens.
No, I've mentioned Professor Lance. Professor Zainal Hasibuan, the chairman of Apticom, and then at the evening we have Dr. Beno Pradekso from Sulawesi 247. That is the essentially what will happen hopefully throughout the day. I hope everyone stay tuned on this event, and we hope the whole speeches that we will hear today will give us inspiration and good for future works and collaborations. So with that, let me end the opening session. Thank you very much for your attention. And we will have a short break, roughly 5 to 7 minutes, and we'll be back in the next session. Thank you very much.
That's true.
Okay. Good morning again.
Morning.
Welcome back to ICACSIS and IWBIS 2020, the second day. And for the second day, we have an array of plenary speakers and keynote speakers. So for the first keynote speech, first keynote speech, we will hear from Professor Toshio Fukuda, IEEE President. And this speech will be moderated by Professor Wisnu Jatmiko, the IEEE Indonesia Section Chair, and also Professor at Universitas Indonesia. So without further ado, I'll give the time to Professor Fukuda and Professor Wisnu Jatmiko.
Thank you, Dr. Adila. First of all, I will open and introduce the Professor Fukuda. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Thank you very much for being here. It is a pleasure to meet all of you at this international event. My name is Wisnu Jatmiko, the moderator of today's plenary event. I am very pleased to see you here, and I would like to welcome all of you to this prestigious conference. Okay, I will introduce the plenary speaker of this session. He is Professor Toshio Fukuda. Actually, he is also my former supervisor, PhD supervisor, my mentor, and now it's very special because when he become a president of IEEE, and also I become chair of IEEE Indonesia section. Now, I will introduce Professor Toshio Fukuda. He's a BS degree from Waseda University and PhD from Tokyo University. And actually, many awards achieved by Professor Toshio Fukuda, we cannot mention one by one. Okay, without any further ado, now please welcome our plenary speaker, Professor Toshio Fukuda, with the title Robot and AI, BI, and CI. Please, Professor Toshio Fukuda, you are welcome to present the presentation and do the share screen. Thank you.
Hi. Halo.
Halo.
Hello.
Terima kasih.
Hello.
Terima kasih.
Terima kasih. Selamat pagi.
Selamat pagi.
Selamat
Thank
pagi.
you very much.
Arigato.
Adila-san. Ya, terima kasih. Adila-san, thank you very much to moderate all the things, opening session. Also, thank you very much. Wisnu-san, thank you very much. You are doing a good job as a ITP section chair. Nia-san, she also helped me to do so in many ITP activities, including education activities. Ladies and gentlemen, distinguished delegates, my friend, my colleagues, I am Toshio Fukuda, ITP President 2020. On behalf of ITP Board of Directors, as a President of ITP, I would like to congratulate you all in IWBIS and ICACSIS 2020. Now I'd like to share my slide, PowerPoint, with you. Just a moment. Yes. So today I'm very happy and I'm very pleased to see all of you in Indonesia. Since I visited Indonesia more than maybe 15 times, but not 20 times yet. I'm very happy because I'm proud of Wisnu-san. He was my PhD student. That's great to have such a wonderful, brilliant guy as my PhD student from Indonesia. Also, I had many later on such a PhD student from Indonesia following Wisno-san to Nagoya University. So this is me, Toshi Fukuda. I'm president, and I was 20 years ago. I was president at the Robotic Automation Society as the first non-US citizen to be that. So, as you know, I'm now president from Region 10, also, Asia and Europe for the first time. I will do something first, okay? First, I2P Robotic Automation Society as a non-US citizen, also like such a kind I2P president this year, not from US, from first one from Asia and Europe, as I said. Also director, Division 10, 2001, 2002. This I am also first one as elected outside of US. That's I always do something new. So that's a kind of, that's our DNA to Wisno-san, okay? That we'll do always something pioneer, do something new, okay? So also I created fund I2P Nanotechnology Council, 2001, 2002, 2005, because I felt I working nano robotics and somewhere to do some work. That's great to make such a kind of new council, technical council in I2P. That's also nice to make it by myself. Also created here something like kind of such a kind of transaction mechatronics here. This I created 1996 with my good friend of Tomizuka from Berkeley and Professor Fumio Harashima, University of Tokyo, together. We made those things so that we can create new journal in I2P. You can do as you like it. So that's again, I like it, many things. And I was so fortunate to have such a good PhD student, 104, including Wisno-san. And I could write many papers with them. Very happy to do so. That's my works. So far, like a monkey. Oops, it doesn't work, it doesn't matter. So anyway, that's a many things. Like here, a monkey type of thing. Here, this one, I tell you, also this moving. This is a kind of actuator from biocell, just a kind of new muscle like that. And also nanotechnology here. I tell you why I'm doing something like that. Back to 40 years ago, I started with such a kind of cell, mechanical kind of unit, like a kind of biological cell come in biological system. We have a cell, and we make a kind of tissue, organ, animal, group, and society human being, for example. Why not we make such a robot system like that? So I made such a kind of unit of a robot, make a kind of a module, make a robot, and group of a robot, then many robot, sort of a society of robot being, something like that. Okay, that's I try to do so. So I make those things when I was young, 40 years ago. I'm very brave to make those things with my student, working together with such a group robotics or some kind of monkey type of thing. How you make a robot intelligent, or something like a millimeter wise, how we can make a medical robotics. So with a sub-millimeter technology, then we make such a kind of micro nano robotics in micro nano scale. That's a kind of something new to those. And I had so many good students, PhD students, like here, so many here. Wisdom starting from here. So somewhere, Wisdom must be somewhere. Go like that. Go that here.
Jatmiko in
Here, somewhere.
63, Prof.
63. So me here somewhere, right? We come here. Somewhere.
Next. For more. This one. Yes.
He, Wisdom is here. This is my people working together. They are graduated from lab. They are so brilliant. They are my colleague working together in kind of research topics. That's a kind of thing here. Today, we have we are in a difficult times. As you know, we have a coronavirus pandemic that's going to cause a lot of problems. That because of that, we have to change our mode of life. Like here, this conference is a virtual conference. Instead, conference in person. Okay, so here we can have something here that kind of coronavirus. Well, the many kind of wise scientists made many contributions to this field. Now they are working on such a vaccine here. Okay, so also like here we have a kind of checking how to prevent such a spread of such a coronavirus. So that's we have a CPR. That's testing those things. Those technology is kind of our I2P technology. Don't worry about those things here. We have such a kind of electronic technology here. We also have a kind of simulation using a computer, how we do like that. Also like kind of we can tracing by using a mobile smartphone. Okay? Where the people, where? Like we can trace those things to prevent such a spread of corona infection. Also with delivery, that's now new mode. We try to avoid such a contact. Then we can order something by Uber, like that, like Amazon.com, wherever it is. Also, we have entertainment, electronic entertainment. Also, we also have e-sport. Since we are staying at home, we need something new. So now we have a new normal. That's okay here. So we can have a kind of a virtual things such as shopping, school, university lectures, also business ways, or many things. Now it's a kind of new normal, different type of thing here. So before and after the coronavirus, that's a kind of somewhat like a vulnerable physical global system. And we are now moving to virtual environment tool and system like this Zoom tool to make this conference possible. Then we are accelerate virtual society now. Maybe before such a kind of coronavirus, we didn't know where to go. So that's great to know. We can reconsider what to do, something like that. How to make such a kind of strong physical global system, how can you make use of virtual environment, how we can accelerate virtual society, something like that. That's a kind we have to think about. We have many things to do so. And that's a kind of, one of them is robotic technology. Robotic technology can help how to do that. So once again, this is a multi-scale robotic system, what I used to work, I'm still working on. I like it, this one. And then we have a corona here, that we have a kind of a PCR in the level of micro nano level here, then come up here, such a kind of sampling. So sampling here, like here. So sampling from the nose, also swab sampling here, then we can make this type of thing to avoid such a kind of infection by using robot to take care of those things. So that's another issue here. And then we can prevent such an infection spread, such a kind we can we can deliver many things here by using such a many multiple robotics here. So that's great to do so. Then this year, I was a president IWBIS, and I was in New York till mid-March, and I escaped mid-March from New York to Japan. Yeah, that's to avoid infection. My research work is, as I said, such a multi-scale robotics from nano to multi-robot. So scale-wise, this is kilometer-wise, millimeter-wise, or micrometer-wise, nanometer-wise. That's many things going on. That's great. That's a kind of, actually, our such a kind of virus, coronavirus is around here, 0.1 micrometer. This area that's here we are talking about. Okay, so robot here. We just talk about 4.0, 5.0, 6.0, something like that. That's a kind of evolution robot. As you know, robot is started about 50 years ago. Robot 1.0 as an industrial robot. Robot works in the factory. Robot works some other here, day and night. Okay, robot 2.0 service robot. 1986 here come up here that can help people to do so. Besides industrial robot, robot 3.0 come to the as a personal robot in 1997. Like kind of such a biped robot, or kind of other such a kind of entertainment robot, something like that. Then robot 4.0 as a network robot in 2010. That's here. Robot 5.0, maybe 2025 or 2030. Robot 6.0, maybe 2045 as a year of singularity. Singularity means the machine intelligence is better than human intelligence. I don't want to do so. We would like to ask or request many students study so hard, better than machine intelligence. Anyway, this is broad, wide, and too deep to do so. Like a robot 1.0, as you know, this arc welding to painting here. That's a kind of robot working in industry, particularly automobile manufacturing assembly system here. Another one is we need a more autonomous driving car, particularly under Corona, because that's a kind of autonomous car is very convenient to deliver many things automatically. But we have to pay attention. We need a safety. We need a kind of good standard to make it possible. Anyway, as I mentioned, robot 4.0, 5.0, 6.0. What is it here? In the hospital, there are some robot behind. When we're sleeping, someone is here behind. When we are in the park, someone outside of the office here, or inside the office, there's something here behind you, or in the home, there's some here, or inside the house, there's some behind you, or even driving here, some here. So you can find many such a kind of avatar for you to help you to do so. That's a kind of time. And you know, I like the Mark Lebert, my good friend in Boston Dynamics. I like this kind of a robot. Very nice. He's a kind of, he was CMU, Carnegie Mellon University professor, then MIT professor. Then he founded such a kind of Boston Dynamics. There's a number of people working together make this type of robot about more than 30 years ago. Another company has a kind of employee, more than 200 people working on those things. And one time it was bought by Google company, but they don't listen to the Google, then they're out of the Google now. That's nice to have such a kind of nice robot to do so. It's kind of very look like show you us such a nice thing with a kind of mobility way. Also showing such a kind of real-time collision avoidance system here. That's great. Also, because of four legs, we can climb up such a ladder, kind of steps here. That's nice to see that. That's great to see that. This type of was so nice to see today. Okay? Now, we can see in the future, we can see lunar cruiser on the moon. That's nice to have those things. That's a kind of inside is a car. You can see, you can enjoy staying inside. Okay? Energy-wise, solar panel, they can collect the energy to do so. And they do work here. This type of mobile car, mobile robot must have a good, robust capability against temperatures, against such many things. That's important to do so. That's important. Also, like here, maybe in 3 years, you can have this type of sky taxi, like that. That's a nice sky drive. That's nice to do so. This is a kind of research work in the relationship of a drone. That's nice to do so. So we dreamed we can fly to go somewhere to somewhere. Like same, we can now, it's coming true to have such a kind of a vehicle soon in 3 years. Also, this is a kind of a robot here hung from the ceiling, so that here robot can deal with such a cooking, something like that. That's a kind of many things, washing, cleaning, all the things in kitchen, for example. It's also good to have those things here in future. Maybe there was so many kind of similar work so far, like washing dishes, or many things. And on the, sometimes it is on board, sometimes from the ceiling, something like that, like a kind of medical robotics here, like that. Also, like today, you can see many such a kind of wearable robotics. Wearable mean here, where we can have such a robot here, who can wear those in here. So she can lift such heavy kind of patient and help them and support them to do so. So this is something. And this is also, this kind of wearable robot was also invented, made, and produced by my former my student. That's great to have those in here. Well, I mentioned about avatar already, long time, many things. At home, office, driving a car, or outside, but it coming to maybe true in the future. That's a robot here, come up here, like kind of telepresence wise, the robot might be there here. Also today, such a drone is very, very nice. They can use drone delivery for medicine. That's nice. They are working on those here, where the medical doctor was out or is not easily available. So they can deliver such a kind of medicine, drug they need, and like that. Now, in the futuristically, that we can have such a kind of robot, such a kind of drone robot on hand. That's a those things, and still it look like kind of toy, but going to be more interesting for the application of medical and also biological system here, also many others. Those robots, what do they need is such an intelligence. Mechanical structure may be okay. We can make it more and more, we can develop more, but we need such a kind of intelligence too. So mechanical structure, smart structure, and intelligence get together. Then we can make a nice robot like that. That's why we need the artificial intelligence, AI, also our intelligence, or animal intelligence, such a kind of biological intelligence, and also computation intelligence, hybrid computation intelligence. As you know, such as deep learning or neural type of thing, that's a self-organizing learning system here. It can apply to image processing, such as pattern recognition or planning control. That's today, face recognition using a lot of those things here. So that's the kind of thing, and that today deep learning or before we often use reinforcement learning here. That's nice to have such an evolution computation too. So when you look at here, that's a kind of AI, artificial intelligence, silicon technology-wise here, and robot here, robot here, and the human here, and AI here. BI is here, that's a human here, human, then kind of our brain, kind of biological brain here, like that here. Like a dog, for example, they are very good to detect such a kind of smell, medicine here. That's a good thing. We are using biological sensing and intelligence also. Combining those things here and BI, we can have a hybrid CI, computation intelligence, that's it. Robot, human, robot, or something like that. That's a kind of a silicon and biological system together. We can see how we can do that. You know, we are learned many things from the past. Computer powers like that, or can such space ways today, because of computer power, we can have a big such space, big data here, like here, okay? But on the other hand, also we'd like to have a small data for education-wise, experience-wise, knowledge-wise. So that's is a big data or small data, that's a quality, quantity or something. Make it with that. Also like a fusion with a meta knowledge, symbolic knowledge, like that. It gives us such a reasoning or explainable AI, like that. That's nice to think about, and should be work as a real time. And I mentioned those things back to 1994. So that's great to think we can make use of such advantage. So multi-scale robotics here. When we talk about many robots there we can talk many robots work together here. Such a kind, I wrote a book about such a several robotics back to 25 years ago, such a can see here. This is a kind of a conceptual pictures, communication with a robot here, and work together, two robots work together to carry heavy payload here, or something wrong, exchange something like that, okay? So to replace with something. This is a self-organizing manufacturing system here, flexibility-wise, self-evolutionary-wise, self-repair-wise, self-congregation-wise. That's great to have those things here. So I made a kind of basic research work, 1984-5, when I was a young associate professor in Tokyo. That we started those things here. They're nice. Then made those things here. That's kind of in Nagoya. So this is something like here. That's a kind of thing robot. Multiple moving around. Nice to have those things here. So they are working together. They need a communication. If the distance between robots exceed more than 10 meters, the communication will be disconnected. When they try to move together, they have to keep such a distance too. That's interesting to do so. That's a kind of interesting, such a kind of problem. So I demonstrated such a kind of concept of multi-scale, such a self-organizing manufacturing system. Here, the kind of material come here, the material here come here, then material go here, such a kind of handle here, now next here, handle here, the next handle here, the handle here, handle here. In this way, eventually it go out like that. This is a pallet here. The part move around here, so they can deliver those here. They can make such a kind of two-dimensional type of manufacturing system. It is suitable for different type of small amount of production, not for mass production. This is an example that the flex transfer system here, back to 25 years ago, it has a kind of
FTS was developed with the intent of providing just-in-time transportation of the required objects to the required places at the required time.
Transfer for full
At the same
direction.
time, the goal
Also,
was for
module
FTS
self-organizing
to be an autonomous
production system
transport
here.
system
It
that
has
could
a
adapt
kind of
flexibly to
characteristics
breakdowns or
for-
changes in the
for
manufacturing environment.
automata or genetic
Features required of a
optimization.
flexible, just-in-time transport
Something
system
happens,
include the ability to
change
transport
the
multiple
composition to
objects
do so.
in parallel without
That's a
collisions,
great thing to do
and not
so,
being limited
and
in
to have
transport direction.
such a, so
Such a
this
system
is
should
an
also
easy
be able to respond
reconfiguration.
autonomously
They
to
can do
changes in the
that.
manufacturing
Oh, that's
environment
nice
and
to have
be
those
easily reconfigured.
automatically do that. We can help
To
those in here,
realize the
okay?
required features,
Prototype of
the
FTS.
FTS
This
prototype
one,
was composed
something
of
wrong,
FTS
maybe we can do
modules
that.
and
Okay? So those concepts was introduced to some industrial kind of production system here. Concept-wise, there's a kind of line of product produce such a kind of electrical assembly here, and such a kind of here robot 1, 2, 3, 1, 2, 3, 4, 5, 6 is here. That's a robot here with same kind of configuration. Manipulator on top here, that's here. Same software. So they can move around here, they can assembly such electric part. Once the demand is more, the robot come more. If the demand is production is slow, then those some robots go out. Still, they can keep their production system. Okay. You have a Kiva system. This is very popular, and because of kind of a warehouse.
They are fast,
Simple,
they are strong, and the color avoided crush. These machines were created by Kiva Systems, a Boston area startup that wants to reinvent the warehouse business using robots. Lots of robots. Kiva's idea is simple. By making inventory items move instead of the workers, they can fulfill orders faster. In Woburn, Massachusetts, Kiva set up a warehouse to demonstrate the system.
Once I submit that order in, it understands that I'm ready to fulfill that order. So it prints out a label for that order. I build a box that I want to put that order into, and it asks me where I want to place that order onto my shelf. I'm going to say right here. Now that I've placed that order on here, and I can place up to 6 orders at a time, the system is going to go out, find that inventory, and you can see it's already starting to bring that inventory over to me, so that I don't have to go and find that inventory. It goes in, and the inventory comes to life and starts coming directly to me.
By Amazon.
So the user.
In such a way, there are many kind of idealistic research work, and also many kind of compromise with such a kind of robot or human together, or the more practical way like that. There are some levels there, but you can see how we can put it. We can make a research work to move to those things. So now usually robot has only one function.
After the motion learning process, the robot can locomote from branch to branch, forward and backward.
The
posture of the robot is measured by gyroscopes built into the arms, and the joint angles are measured by encoders. The robot is calibrating its gripper position and closes it when it approaches to obtain better motions.
So they can do that.
After the motion learning process, the robot can locomote from branch to branch, forward and backward. The posture and the joint angles are measured by encoders. The robot is calibrating its gripper position and closes it when it to obtain better motions. After the motion learning process, the robot can locomote from branch to branch, forward and backward. The posture of the robot is measured by gyroscopes built into.
So anyway, this is kind of multi-locomotion robot here. Yes, there are some like animal. Go up, or bargain, or climbing, something like that here. They're nice to have those things. So I made such a kind of a model of such a robot to biped walking, or quadrupling, or climbing, or bragging. That's nice to do so. We call MLR, multi-locomotion robot. That's nice to have those things. This idea, kind of symbolic one, try to make a robotic zoo. So I went to a zoo in Nagoya, and I saw this one, and this is a kind of a skeleton. And that made so similar one like this. 1 meter height like that here, they made it. Now the robot here, we are doing something. It was something like ladder. Nothing. Collaboration. So anyway, this is kind of interesting. Since we have so many locomotion modes, how we can select such a locomotion method? Which one better? When you're walking here, maybe biped is more kind of efficient, but when it comes to the kind of left line, maybe not. Oops. Well, so that's better. Stability-wise, we can select it. Which one is good? Which one is good? That's a kind of value of locomotion. So locomotion reward computing in a way, such as stability-wise, way of locomotion-wise, that's here, robot move around here. So they can come up here, okay, the biped detect such a kind of slope here by laser range finders, then they can change the locomotion mode like this, walking 4x4 bed, and climb that kind of 20 degree of slopes. Suppose this one move around here like that, maybe flat is okay, but if come up here something like that, no good. So that's why they try to change a locomotion ball. That's here more like such a quadrup here. That's nice to keep the stability like this. Anyway, this is something like that, interesting to such a kind of a total risk value, speed of efficiency, adjust the speed wise, you can move here, biped, change the priority bypass to other, something like that. So that's nice to do so. Also, like I work with those kind of multi-locomotion robot. I like this kind of IWBIS system here to help people in sub-micron, sub-millimeter type of technology. That's nice to have a simulator of intravascular surgery. So that's kind of, I made this thing here. Then we can come up with a much better simulator, super simulator, maybe 10 years later here. That's nice to have those things here because something happened in your kind of brain or blood vein, you might have some problem here. To keep your kind of quality of life better to have a better conceptual surgery. Then the surgery must be done by medical doctors. Medical doctor must have a good skill, better skill, best skill. That's right, to survive you or in case you are in danger. Okay, so that's why somewhat here. If something happened here, neither such a kind of a clipping here. If you have such a kind of also like here, need a kind of a stent here for diabata, something like that. That's important to do so. So but somewhat there's always some problem. That's why we made such a fractal stent. That's our kind of stent here. We can make such a stent better than others. So also it's a bionic humanoid here with my former PhD student here. Now he's a professor of University of Tokyo, made such a bionic human here. Now we categorize micro nano, such a kind of research work here, millimeter-wise, micrometer-wise, nanometer-wise, dry, and such a wet way. Wet means biological application. So that's here we can have a force sensor-wise, or kind of force sensor, much smaller one, or such a kind of nanostructures like that in nano level. In bio level, we can make this kind of biodegradable scaffold or blood bank, or maybe other kind of chip here, also make such a kind of biological system here. Okay, so that's a kind of biosynthesis-wise in biological. We try to make such a kind of biosynthesis from bottom to top, like a non-silicon system here. Why not? We can make it in between. We can make a hybrid one. That's what we can talk about. Okay, so we can form bio, or just simple cell. We can make assembly, 1 degree freedom assembly, 2 degree freedom structures, 3D freedom of structures. How we can make it? Like here, we just make kind of seed of a cell, seed cell. Then we roll up here like a sushi roll, Japanese food, sushi. Then we can make something like that. Okay, so this is nice to do so, or do something like that. We can many methodology. So 3D assembly based on material robot here, we can inlet such a kind of cell here. The cell, we can select the cell, good or bad cell here, select it here. Then we can incubate it, put it here, such a kind of cultivate. Then after cultivation, we can harvest them, put it back here, so that we can keep good. So see, there's many methodology here, application-wise here. We make such a kind of blood bank, or kind of many other like here, such a kind of liver structures here. So this here can decomposition here. This is a kind of manipulator system here. So what we can do? Now I can tell biointelligence. This is a kind of C. elegans. C. elegans is just less than 1 millimeter. But this has a kind of good sense of sensing chemotaxis. including cancer. If you bring your so you bring uris, your PP here, we can dilute 1/10. They can bring it here. Then, if the silicon goes there, it's a somewhat kind of maybe cancer. If not, no cancer. You can screening such a using such a kind of intelligence or bio such a bio. I call biointelligence, BI, like this. Okay, so that's nice to have such a silicons. That they move here. That's nice to do so. Also it's a one. This is one. Okay, we can make a here, do something like that, or do something like that, something like that. We are dealing with such a small less than 1 millimeter scale put here using such a capability of sensing like that. They can sense better than dog nose, something like that. That's nice to have those things. So why don't use such a kind of AI and BI, our biological kind of intelligence? So we can make a cyborg type of thing here. So here, something enhanced sensing here, or enhance the sense, smell, using those things, or sound noise, or energy supply, or we can have such a kind of artificial organ tissues here in hybrid ways and super protection here like that. Then we can have a mass strength devices. That's kind of such a kind of structure here. An animal get together. This is integration, fusion of such a kind of silicon, non-silicon together. So later on, we can connect here with a neuron interface. And that's connect here, we can do that. That's a good technology necessary for cyborg hybrid system. And here, we can have a kind of a system level here. You have something on, you can have something here. Or in more detail-wise, group here, some muscle missing here, muscle strong, not what kind of here, joint something on. We can talk about those here, develop such a in device level here, even more about, we can have such an individual here, biosensing. That's a bio level here. Just kind of bio level. We can make such a here, as I mentioned, such a create such a kind of muscle from a bio cell, C12, such a kind of sensor, bio cell, we can do that. So that's all right. So that's nice to have those things. So we have kind of artificial cell muscle also here like that. Also we have kind of many artificial teeth, many kind of leg, arm here, joint, hip joint, proper more than 30 years here. We have an artificial heart here. So that's a kind of thing where we can ask people to live in good way, such a they can keep such a nice life here. So to do so, we have such a micro robotic here, magnet tweezers here. We can do that, something like that. We can do that. Nice to have those in here. Make such a lever model. That's a kind of 3D here. One layer, second layer, third layer here. Then we can have a blood vein here. Why we can make such a blood vein system? Because it's we can fabricate such a kind of a cell. They need such a kind of blood vein to keep their system there in such a level, also grow more. That's why they need such a blood vein. That's okay. So we can make blood vein and for the liver. This is can fabricate hepatic lobule structures, later on become a liver. Okay, that's nice to have those here. That's a good work here so far. So also like here, as I mentioned here, there's a muscle moving here. That's nice to have those things here to do so. So great to have those here with those things here. Anyway, sometimes you need one more arm, or you need two more arms, something like that. Okay, this is a hybrid here that you just put here, but this put here doesn't mean good enough. You need an embodiment. They have to move as you like. Okay, embodiment important. If you do by yourself, controlling this hand, okay, by your hand, no use of your both hand. You have to make use of three hands functionally. How do that? That's important to do so. Okay, that's why we need such a kind of embodiment. Okay, this is a hybrid system here. Okay, this is very important to do so. That's also this is one part of cyborg. Okay, research bionic system, hybrid system here. Okay, now we have a kind of moonshot program 2020 to next 5 years, AI and robot. I'm a program director. My goal is how to make a robot good, autonomous, learn, adapt to the environment, evolve itself, intelligence, act with human being by 2050. So that's why we have to backcast to from 2050 to 2040, 2040 to 2030, 2030 to 2025. What to do? What's the problem there? And we can make those things here by 2050. Develop AI robot that human does not feel uncomfortable, have physical ability equivalent to or better than human, and grow with human life. That's important to do so. Second target, so by 2050, development of automated AI robot system that aim to discover the principles and solutions by thinking and acting in the field of natural science. That's great to do so. It depends level 2050, 2040, 2030, 2025. Okay, this is way we can make such kind of good research work here. Third target is by 2050, the AI robot that autonomous judge act in environment where it is difficult for human to act, like a moon. Okay, on the moon, we like to make such a kind of a house for us to live, for example. That's important to do so. It's a different technology, but we need such kind of robot technology by 2050. And to do so, we need such a robot step by step by 2025. Any AI and BI and CI, Indian robot system, that's nice. And as I mentioned that machine intelligence AI, today we can have a much better AI, not just a simple deep learning. Okay, also we have a biological intelligence here. Also we have a hybrid computation intelligence here in between there, and that's a thing. Yeah, in a sense, supercomputer and also human brain get together, do something, have a good reasoning here. And cyborg, hybrid, not only physically, but also way of thinking, that's great. And particularly I like empathy and thoughtful AI. Not just a kind of AI, but thoughtful AI. And we'd like to work together to advance technology for humanity. Thank you very much. This is something like that. Our great father, okay, Isaac Newton mentioned, no great discovery was ever made without bold guess of a human. There are even more. If I have seen further than others, it is by standing on the shoulder of a giant. That's a nice to learn. We should cooperate together in the world. We are the research scientists and professor, whoever it is, Okay? All the world, we should get together. We have to work together. Such a kind of such a scientific or technological achievement should be shared by many, many people. There are no boundary in the science. That I want to mention, sir. Thank you very much. Once again, IWP, as a president of IWP, I'd like to say thank you very much. All the leader of to both conference, and particularly Wisdom-san, thank you very much. That give me such a good opportunity to me to talk about it and also to work together. Terima kasih.
Terima kasih, Professor Fukuda. Is very impression talk. So I just got the new energy from you. Even I.
You do that.
Every year I visit to Nagoya. Actually, I want to got the new energy. Now, even with the virtual, I still got the energy. Okay, let's give a big applause to Professor Toshio Fukuda. Okay. Now we will start in the Q&A, and there is some question from the audience, Prof. Fukuda. Actually, I will make some cluster, and because the question is quite similar, maybe at least 3 questions, Professor.
Okay, go ahead.
Fukuda. First one is, for example, first, can the robot become, I don't know, replace the human, or can become a clever, or like last night discussion with the Professor Anil Jain, it is possible, and when that time? This is the first question. Okay,
robot,
maybe
what robot, part of a robot, part of human, what the
can
human
replace the intelligence of the human
itself.
Yes, human itself, and the robot, it can clever and can intelligent the human. It is possible, or is there any direction for that research? For example, what is your opinion? This is the majority of the. Okay,
come on, you know, Wisdom-san, or many ladies and gentlemen, by 2030, today's job 27% gone. Don't think we still keep such a same work of 27%. It will be replaced by machine intelligence and robot. 27%. Mean 27% gone with a robot. Even 47% of work, today's work, will be replaced by robot. Okay? That's again simple work, like a kind of a cleaning, for example. That's in the whole, it's already replaced by robot today. That's a kind of dependent environment, dependent thing. So like a kind of I should say, like I say, 2030, 2040, in an area which we a special area, maybe that's automatized by such a kind of robot cleaning and also kind of whole thing. And 2050, as I mentioned, we can make such a kind of a house made by multiple, many small robots. That's a possible. That's what we are aiming at in my project 2050. This is the first one. How's the second one?
Okay, thank you. And the second one, because you talk about the AI, BI or CI. So the meaning is the computer research field. Maybe your can you stop share
I think there's some
screen,
kind
Professor
of
Fukuda, so that maybe the bandwidth.
Internet speed problem. Can you tell me once again?
Yes. Maybe. Okay. In your presentation, you discussed about the AI, BI, and CI, and the meaning is your direction research or the next direction research is related with the computer science people, isn't it? For algorithm, how to make reinforcement learning, for example, become to make a distributed algorithm. This is true, or what is your opinion?
I cannot catch the word clearly because of some kind of internet speed word. But the learning, for example, that's very important to do so. So AI, of course, and machine learning today is no more available. That's an old-fashioned in 2025, 2030 already. Okay, so we need something new. Also, we are human being, or we are such a kind of a biological system, like a dog, your dog, or you kind such a kind of you are kind of insect, or you kind of see elegance, even such a small one, less than 1 millimeter. They have a great intelligence. That's a biological intelligence. Why not make use of them? Like that's important to do so. That's again, I just mentioned as an example, how to detect such a cancer. Okay? You have to make a lot of research here to do so with many data needed to for AI to decide. But you just simply bring one small insect to your urination. they can tell you roughly, okay, not exactly, but roughly you are okay or not okay in cancer. That's a kind of, why not make use of such a biological kind of intelligence? So also like that, our kind of body very kind of delicate. That's here. So that's why we can make use of such a kind of our body too. So that's why I say AI, BI, CI, such intelligence, learning capability important. Also like we human learn from robot too. That's important. It is called transfer learning from here to here. There are many ways of transfer learning. Transfer this learning here, one to other kind of purpose. Also, we learn from robot too. So that's a kind of thing important to think about. That's a kind of learning. It's a very important, and we can depend each other, robot and human. Yes. Did I answer to your question? I don't know. Hey, freeze.
Okay.
Someone freezed.
Okay, maybe Mbak Nia, can you clear listen me?
Somebody raise a hand. Hello.
Mbak Nia, can you?
Hello.
Hello.
Because I don't know.
The internet.
Can you hear me?
Yes.
Some Zoom is kind of freezing. Okay.
Can you, Professor?
We can hear you perfectly.
Okay, great. That's great. Go ahead.
Okay, maybe
next question. Third question.
The last question.
I had the one, first one, second one. I need the third one.
From the panelist. From the third one. From the panelist.
Hello.
Hello. We will choose. Pak Dila, can you hear me, Pak Idris? Because I don't know. Also, my connection is not stable.
Can you hear me?
Yes.
Yes, we can. Yes.
What's the third question?
Okay, I just.
Okay, Pak Bisen.
Collect from the Q&A, Professor Fukuda. This is the interesting about the
first one, second one, third
okay,
one. Third question.
Interesting about the nano. The third one is how about the energy from the robot? Because when we implement in the real robot, we use we must create the energy automatically. How to deal about that?
Hello, Professor Fukuda, can you hear us?
I can hear you. Go
okay.
ahead. Go ahead.
Okay. I think, Pak Wisnu, I'll read it out. Okay.
Okay.
Go ahead.
So the third question is about energy. So you mentioned a lot of micro and nano robots. How do these robots get energy? Are they using like ordinary batteries, or do we need something like special for them for the energies?
Yes, very nice question. Very important. Today's robot has a many problem of energy. Even drone, you have a drone, okay? They can fly a couple of minutes or 10 minutes, something like that, okay? With a battery, electric battery. They need a kind of, they need such kind of, not battery, but the engine. That's a kind of another issue, okay? But if you go to such a kind of a biological world, it's different. Our computer using a lot of energy, okay? Heating up. Even your PC, you have a kind of problem of some kind of effect, okay? So that's a speed limited by the kind of thermal limit, okay? But our brain, at most, it what, okay? Even you are working on so great, maybe 20 watt, or something like that. You are not using a lot of energy here. So why don't you use such a kind of biological kind of such a thing here? So that's another issue. Today, last year, our colleague of a major university, professor, received he received a Nobel Prize of lithium battery. Lithium, okay? Lithium battery is so nice. But think about it. Your PC, even like kind of say autonomous driving. Maybe you are using NVIDIA system. It's hitting a lot of kind of energy, okay? It's a lot of things. So that will not be applicable today's automobile cars because of a consumption of electricity too much. That's why. So to do so, we have to solve a problem of energy. You're right. How we should think about it. Okay, we have to work on such an energy sources. What to do? Then that's why I'm looking at such a kind of not only AI, but the BI, such a lower energy, slow maybe, but a good kind of code of such a kind of prediction and of reasoning. That's why we need those things, combine both of them. That's a kind of hybrid computational intelligence, what I mentioned. Thank you.
Okay, thank you, Professor Fukuda. Pak Adilah, because the time I think is because the time, Professor Fukuda, actually there is.
Okay.
There is. Yes. Okay, Professor Fukuda. Because the time.
Terima kasih. Selamat.
Yeah. Hello.
Hello. Good.
Yeah, I think Professor Wisnu Jatmiko's voice does not reach Professor Fukuda's.
Oh, Wisnu-san is now muted. His microphone muted, so that's why.
Oh, okay. Okay, I see. I think I can hear. I think there might be a connection problem with Professor Wisnu Jatmiko.
Okay.
Yeah. So, Professor Wisnu, I'll just read it. So, shall we end the session?
Okay. Thank you very much. Terima kasih.
Yes, terima kasih Professor Fukuda. let's give Professor Fukuda a round of applause. Yes. Thank you, Professor Fukuda, for the session. Pak Wisnu, yeah, I'll continue with the next session, I suppose.
Okay.
Thank you very much. Terima kasih.
Yes.
11, isn't it?
Yes, 11. So we have 10 minutes. We have roughly 10 minutes. Okay.
Pak Adila will inform the audience.
Okay, then I stop my sharing, okay?
Yes. Thank you.
Thank you, Professor Fukuda Sensei.
Thank you, Fukuda Sensei, for the talk.
Thank you, Fukuda Sensei.
Nia-san, bye-bye.
Bye-bye.
See you in the afternoon, Professor Fukuda.
Yes.
Okay, on the agenda.
I go to lunch.
Yes, it's lunchtime.
Professor Fukuda, I send you in the email for afternoon events, different Zoom link.
Okay.
Yeah.
Thank you.
Thank you.
Thank you, Professor Fukuda.
Thank you, Professor Fukuda. All right,
Terima
so
kasih.
ya,
Bye-bye.
terima kasih. Ya, arigato gozaimasu.
Ya, terima kasih.
Yeah.
Bye.
All right. Okay. So, ladies and gentlemen, thank you very much for your attention in this session. We thank Professor Fukuda for the powerful, inspiring talk, and I hope everyone gets positives out of it, and inspires everyone to, well, on their work and get more advances, and do more to the society. Um, we apologize if not every question can be answered, but at least hopefully with the presentation and the subsequent discussion, we some of the or the majority of the answers, because majority of the questions are answered, because a lot of questions here are very similar. I thank you also, Professor Wisnu Jatmiko, for moderating the discussion. For the audience, we apologize if there is some glitch in the connection. All right, so we have several minutes before we move on to the next the next plenary speech, I should say. So let me just mention, for the plenary speech in the next session, we will have Professor Kook Jin Chun, from Vice President, IEEE Vice President, Chair of Member Geographic Activities Board. We will have a short break while the organizers prepare the display and all. Let's have a break and see you in a couple of minutes. Okay, so we will start in 2 minutes roughly.
Yes.
Okay, we'll start in 3, 2, 1. Time is yours, Prof.
Okay. Hello everyone. Welcome back to ICACSIS and IWBIS 2020. Now we have the second plenary talk. And for this plenary talk, we will have Professor Kook Jin Chun, IEEE Vice President, Chair of Member of Geographic Activities Board. And without further ado, I'll give the time to the moderator, Dr. Kurnianingsih, Vice Chair of IEEE Indonesia section. The floor is yours.
Thank you, Dr. Adila. Hello, everyone. I'm Kurnianingsih, Vice Chair of IEEE Indonesia sections. Thank you for joining us today. I would like to moderate the second plenary talk today by Professor Kook Jin Chun. The title of plenary talk today is Integrated MEMS Sensors in the Age of COVID-19 Opportunity and Challenges. I would like to introduce Professor Kook Jin Chun. Professor Kook Jin Chun is a professor at the Department of Electrical and Computer Engineering, Seoul National University, Seoul, Korea, from 1989 until present. He has several activities, both professional activities and IEEE activities. Currently, he is the Vice President of IEEE Member and Geographical Activity. He is also Director of IEEE Board of Directors. He is also Chair of IEEE Region 10 NNA Committee. And he is a past Director of IEEE Region 10. He obtained the bachelor degree in electrical engineering from Seoul National University, Korea in 1977. He obtained the master degree in electrical engineering from University of Michigan in 1981. And he obtained a PhD degree in electrical engineering from University of Michigan in 1986. He received several awards. Some of them, he obtained the Order of Science and Technology Merit of Korea Award in 2017. In 2013, he received Hidong Awards, Institute of Electronics Engineers of Korea. During these sessions, participants are welcome to have an opportunity to interact with the speaker through Q&A box. Okay, now let's start our plenary talk. Professor Kook Jin Chun, time is yours.
Okay, thank you, Nia, for good introduction, and I'll try to share my file.
Please.
Oops. Yes. And, okay, so can you see my file?
Yes. Yes. Perfect.
The sound is okay too, right?
Yes. Sound is good.
Thank you. Well, hello everyone. Thank you very much for this opportunity for me to talk about the sensors and MEMS technology. And then I really appreciate the invitation to this excellent conference with a lot of participants. Well, I'll talk about some of the introductions on the MEMS technology. Well, the word MEMS, micro electrical and mechanical system. Now that includes optical and biomedical aspect as well these days. And this MEMS word showed in early 1980s. And before then, people talk about the sensors. So sensors and MEMS, are kind of similar words in this area, in the people in this area. Basically, as you know, the sensing is to take or change or transduce the energy from many different types, like electrical, mechanical, optical, fluidic, chemical, thermal, to the electric signal, and then with that the signal conditioning or with the analog digital circuits, then that signal is fed into the microprocessor to make a decision, and it'll go to the actuator for any actions, and for the whole process, the radio frequency signal or method is also combined for a wireless communication. So this is a closed loop process rather than a open circuit, open loop process. And this, I basically, worked on the solid state type micro sensors or MEMS technology, meaning that in the 70s, people think of changing the mechanical sensors to the microelectronic or the electronic, the sensors. And then they thought of using the microfabrication technology, which provides a batch and then very small and low power and the low cost and probably mostly identical performances. So you started with a discrete sensor as in the bottom, and the people started to make microstructures like the ones in the solid state technology, microelectronics. And then, in the 70s, some of the rather large, in the range of the centimeter size, showed up, and then people were trying to use those by replacing the mechanical sensors. And then in the 80s, most of the sensors were for the automotive applications, and it's still being used. And if you, for your car, you can find more than at least 10 sensors now by using MEMS technologies. And the people tried to make a sensor and microstructure and even the electronics, they integrated in one chip in the 80s, and the products came out in the early 90s by Analog Devices. And then, from the 90s, people are looking at the low temperature process. Before then, because it's using a solid state technology, microelectronics fabrication, the temperature is quite high, up to the 900 degree or 1000 degree even, from the 400 degrees. So people are looking at 100 degree or 200 degree of a low temperature process by using laser or other types of a process. And then because it was similar to the IC fabrication, the aspect ratio, the ratio between the X and Y, is a rather small, two or only a few. But people are looking at the tens of a aspect ratio. And for that one, for that etching, people needed a new type of equipment. So it's called the deep RIA machine nowadays, which is very popular in most of the MEMS facility. And then another type of a different technique was used called the wafer level bonding. That the wafer, basically microelectronics uses only one wafer and one side, but this MEMS structure uses both sides of the wafer, and then sometimes the many different types of substrate or wafers. So the bonding became a very important process. And from the year of 2000, people are looking at the use of a nanotechnology and the new material like polymers. And then nowadays, people are working on the flexible or wearable the devices. And then, as in the previous talk, the power is again a problem here because, basically the micro robots in our human body then needs, some kind of power to move along. And sometimes it uses a biological the power system or very high frequency RF type power transmission. But still, anyway, it needs a power. So that's a big challenge nowadays. Okay, the materials basically started with a silicon. So people used the orientation, of the silicon, single crystal silicon. But nowadays it doesn't really care because of the reactive ion etching machine. You can use, basically the quite universal type of shape you need. But mostly it's a vertical type. So you can, at the bottom on the left, you can see the cross section of the reservoir of an inkjet nodule, which is in the tens of microns in its size. It's a circular, the reservoir. And then in the red part, you can see the how that operates. Basically, there is a the heater at the bottom, and when you put a voltage on it, then it'll hit, and then it'll make a the bubbles, and with the pressure, it comes out from the nozzle, and then in your inkjet you can find 1,000 nodules of this kind, for to emit the ink. On the right side, you can see the very high aspect ratio, the structure, and actually this SU8 is a photoresist. But if you make a very thick SU8, then it'll make a structure like this. So out of the polymer, you can easily make a very high aspect ratio structure. And on the right side at the bottom, you can see the very exemplary the chip from the analog devices, and it came out. You can see this kind of the die shot, in most of the electronic circuits, the cover page, the textbook, and the size is a 3 millimeter by 3 millimeter, and this chip came out in 1992, and the company, had a really some market, from the 1995. So it took us quite a time. You can see a lot of the analog circuits, surrounding the small size of a sensor, which is basically a comb drive, so-called. So, well, the fabrication is not that easy, but and the yield may not be that high, but still you can make you can integrate the sensors and the or moving parts or the circuits as in this. So again, you know, the like a Samsung Electronics in Korea, you know, thought about well, our I'm sorry, the Samsung Electronics is quite strong, you know, in DRAM and in all kinds of memories and some of the uh, 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 LSI circuits, but they thought of the MEMS, okay, in the early 2000, because you know some of the fabrication facility you know becomes old with the years, and then that they should find out how to you know use those old facility, and for MEMS you know it doesn't need you know like a 12-inch wafer, you know 6-inch or 8-inch is still good for most of the applications. So they thought about this one because in the similarity part, you know, MEMS also require a big initial investment on equipment. It's not like billions of dollars, but you know, it's at least tens of $1 million. And then you still need a micro patterning facility, or you know, so those kind of a very high-end, very expensive. But again, you need to think about the process integration between the sensor structure and the ICs. But again, you know, it's a high value added industry. So people looked at these, you know, from the most of the companies or the solid state technology company. The difference between MEMS and IC technology is again, you know, MEMS deals with a mechanical, optical, you know, biological, the structure or the specimens, and so it needs a 3D type of a structure for most of the application. And then again, it needs IC fabrication and then some of the special equipment or dedicated, you know, to some unit process. And the main problem for the MEMS or sensor technology is that it's rather small production to the IC. So, you know, one type of a sensor or which is a pressure sensor, you know, which takes the largest market is only a few $1 billion a year. So if you think of the investment, sometimes you cannot make a good profit out of the MEMS technology. So that was a real, you know, the problem with you know, big company like a Samsung. But still, they are doing it, and then so that they don't use, you know, the big facility, but still, you know, they are doing it there. So in your smartphone, you can find, you know, a few of these sensors, not all. You know, like from the left, you know, one in the sensing devices like a humidity or inertial, you know, acceleration, or the gyro, right, or pressure, you know, or the tactile, the interface like a haptic, you know, interface, or a temperature sensor or thermal imager sometimes, and then the speakers or the microphones, and then the RF stops, so pitch or tuner or oscillator, and even sometimes you know, display type are also used. And in the automotive, you can find again a lot, you know, many variety of sensors. From the top, you can find the accelerometer for your airbag, and it's a you know, the legally binded, you know, for all the cars, and then INS system, and then a microphone for noise cancellation. and to the left, fuel injection, and the distance detection, and then the airflow, and then the proximity, and then brake pressure, TPMS type, and then the tire pressure and the brake pressure. Tire pressure is a TPMS, and then the corrosion sensor and exhaust gas sensors. So you can find many different types of sensors, okay, in your cars. And then from the 2000, people worked on the this bio type called a lab on a chip. So you can have all the bio labs in a one chip. So, but that chip is not a millimeter size, usually. In the centimeter size in many cases. And since it's a bio, so people use not only the silicon, but use glass or polymer mainly. And then the cell separation or concentration or the PCR so done before the analysis. And because you are dealing with the microfluidic, the specimen, so you need a valve or pump or mixer, to treat the specimen. And then currently people are working on the DNAs, from the DNAs to the proteins and to the other cells. And then again, you need, you need to, get a some electrical signal anyway, from the end. So and again, the battery, the energy is again a one type of a very significant aspect of this. And again, robots has a lot of sensors, like a from the microphone to the sensor, the camera to the other sensors and acceleration sensors and gyros. Okay, the market, well, I think it's in the billions of dollars, from the Yole the report. You can see the at the bottom what is the item here. Well, currently the RF MEMS stuff, like in your cell phone, the excuse me, diplexer or the filters, are made of the MEMS technology nowadays. So for that one, that creates a very big market now. And from the bottom, you can find the inkjet, pressure sensor, and microphone, accelerometer, gyro, initial, then the optical, and the microbolometers, then thermopiles, array of thermal sensors, and the microfluidic devices and RF MEMS, and the oscillators, RF resonators, and then some kind of environmental MEMS, sensors for the environment, and others. So, again, RF stuff is, sees a very big possibility in the future. And this slide shows the players in this area. It's interesting to see that the Broadcom, which is the communication company, makes a top, the manufacturer in this area. So it's very, interesting because Broadcom, recently bought a company making that filter, called F-bar filter for a bandpass filter. And then Bosch in Germany, which is well known in the automotive area, and then ST Micros, and then TI, and then some of the startups, and then HP, and so on. So the again, some of the startups and this well-established big companies are also involved. Okay, from now on, I'll introduce a few examples of these, using this MEMS sensor technology to build a communication tool or a biological tool, or automotive tool. Okay, the first one is to make a transceiver system. And that transceiver, I worked on this with about 16 different types of institution. Half of them are companies and half of them are basically research institute and universities. And the whole the schematic is from the Samsung Electronics. So this the system consists of a 2x2 MIMO type, MIMO type antenna and tunable antennas, with the tunable frequency ranges, and then the so-called front-end module. I'll talk about this, in later, and then the one chip of a VLSI circuit, and then we were using a Samsung baseband modem. And for the RFIC, basically it's a multi-band and multi-mode, and it was good for for fourth generation transceiver, and to provide the wireless LAN and the mobile WiMAX capability. So this chip has a from 2.3 gigahertz to roughly 60 gigahertz coverage using CMOS technology with an RF. And then it provides up to 40 megahertz of a channel bandwidth. And again, a 2x2 MIMO diversity. And then it uses only 2 pins for the receiver and 2 pins for the transceiver, to the transmitter. And then we worked on the 130 nanometer CMOS technology to the 65, in the end, and then and using a lot of inductors there. And for the front end module, that includes the single pole double throw switch, and then diplexer, and then filters made of LTCC technology, or the low temperature co-fired ceramic type of filters, or FBAR filter. The reason for using LTCC filter is that sometimes you need a band pass of 300 megahertz, and FBAR could not generate a over 150 megahertz of a bandwidth. So for the very wide bandwidth, then we shoot this LTC is a rather old to the and the single pole 4-throw switch, and then transmitter switch. The diagram shows 4 different types of a bandpass filter in the center. For this the application, we need the 5.8, 2.4, 3.5, and 2.3 center frequency filter for a European or a Korean or American applications. So the frequency, the center frequency changes a little bit, but not much from these values. So for the we use those kind of filters, and then we also use the MEMS switch for a multiplexer, from 4 to 1, and then still we use the HAMT, solid state type switch for the signal process, the signal transmitting, because of the reliability problem. The one problem with this the switch is that it does not generate a 10 billion the usage out of a single the switch. Currently, people tried and get a up to the 1 billion, the usage, but and another one is the advantage of this MEMS switch is that the loss is very minimal. So compared to the other type of a solid state. So it's quite low loss compared to other types of technology. But the reliability is still a problem. And then, I'll talk about this F-bar structure. FBAR, F-bar stands for the bulk acoustic wave resonator. Okay, so it uses a very thin layer of a diaphragm, and the wave is generated inside of the whole bulk. And at the bottom, you can see the cross section of that diaphragm, with the air gap at the bottom, underneath, and then one resonator, either series or shunt. You can see the very thin layer of aluminum nitride layer, and then electrodes, basically molybdenum metal, on top or the bottom of that piezoelectric material. So the piezoelectric material, which is about 50 nanometer in depth, in thickness. So it's a very, very thin layer, and that generates the acoustic wave up to the 6 gigahertz nowadays. And then the resonator is made of that aluminum nitride, and the electrodes makes a connection, and then again the thickness of the layer is 50 nanometer. Basically it provides a very high coupling coefficient, meaning that the energy transducing efficiency is very, very high compared to others, because there is an air gap which provides the minimum loss to the substrate. Signal, in other technology, the substrate is connected to this resonator, or the thin layer of aluminum nitride, so that the substrate absorbs some of the loss. And the aluminum nitride, there are several types of piezoelectric material, but the aluminum nitride provides a high acoustic velocity, high resistivity, and silicon compatibility, and then thermal conductivity. So it's the best material, by now. And then that resonator, either series or shunt, the odd numbers of resonators, either 5 or 7 or 9 resonators are combined with a series or shunt, scheme called a ladder type, and then it'll make a filter, as in the second picture. So all these devices are assembled, in a basically 24 layers of the materials and in the PCB, so that on top of the about 0.6 millimeter the chip, and basically on top of that, there is an antenna switch and SP40 switch and transmitter switch, and then filters, on top. So underneath, there are other, the passive devices like a resistor or capacitors, and then some other type of LTCC filters underneath. So all these devices are assembled in this PCB, so that with a modem, so that we can make a test. And since at the time the Korea basically that generates a 2.3 gigahertz of a signal, so we need a kind of the frequency boosting scheme, as in this. Okay, second example is one for the ADAS system. That this is a collaboration effort with Computer Vision Lab, and people use a LiDAR or a radar or the ultrasound devices, or many different types of devices for this finding the scheme, and the LiDAR, provides very accurate the signals, but it's very expensive. And the radar, is quite frequently used. It's robust for most of the good weathers. But if it's a bad weather, and then even for the bad weather, it works well. But for a detection of the small object, sometimes it fails. So Mobileye, it has generated a camera-based the distance sensor, and there are a couple of types, but basically it's made of the camera basically and the softwares. So it's good, to use simple algorithms, for finding the distance, and it's in the small size radar. But aligning with cars, to cover all the other areas, and the range wise, it's not a really good choice. So we worked on the aperture type, so-called, so that you have a black box camera in most of the cars nowadays. So if you modify the black box camera, like the ones on the top in this slide, that if you put a one layer of the aperture, then you can make a distance sensor. So usually black box cameras, already have a lens system, and then the CIS image sensors on top of PCB in the barrel. And if you insert that yellow part in this diagram, which is a tunable aperture, and that aperture, can be either small or big in size. And then with those different sizes, then you can get a different types of image with a different magnitude of the blur. And then by measuring the difference in the blurs from 2 frames, then you can find the distance. Okay. So for the design, you should think of the field of view, and then blur difference. So while these equations are well known already from the optics, and so you can use those equations, and then for a specific type of image sensor format, and then like a certain specification for the FOV, and then you can find the focal length of this the optical system would be called the F number. So we tried a couple of different technology, and one is a very well-known LCD type. Well, you know the property of the LCD, and then so you can get a the pre-existing the round shape the openings. You can make a 2 different types of aperture size, either big or small. And then for the second type on the bottom, it's a purely MEMS technique that you use the thermal expansion of a either silicon or a metal. You can make this one for with the silicon material or a metal material. But anyway, when you apply the voltage of a few volt or tens of volt, this called the chevron type of layout, expands so that it'll make a movement of the blade on the left, okay, with the arrow direction. And if you make 5 of these identical ones, then you can create a the different types of aperture, either color in this diagram. So you can find the difference between the apertures on the left and right in the diagram. So that's the basic principle. And the movement of the chevron, mainly directs to the upward position. So it basically pushes, the beam a little bit, a few degrees upward, so that the whole blade, is moving, because this is a silicon or metal in a very thin layers. So the weight is very small. Okay. And then for that one, we designed the lenses for the camera for this specific optical specification, like focal length and the FOV and those specs. And then it consists of 5 lenses, as in the black box camera. And then we put it on this for the testing. We put it on this the PCB board with other the control the ICs. So on the left, or on the right side at the bottom, you can see the assembled the tunable apertures and lens, to be loaded in this car. And we use the LiDAR and the car, the autonomous vehicle at the SNU again. One professor is working on this. And then this car is real, and it's it's currently driving around in Seoul area without the driver. And this one uses a LiDAR, which is a 32 channel Velodyne type. So we basically use the LiDAR as a reference to our sensor, and then matches those with the in a certain distance. And for finding the distance from the 2 basically images, then we use a the depth estimation from the 2 different types of so-called types of mechanism algorithm. One is a detector type, and then for that one we use the YOLO V2, and the ResNet network for the depth estimations. And then for the purely a depth estimation by depth map, then we use the convolutional neural network. So with the CNN, basically we adopted the deep learning technology with a lot of data here, so that we can make a better accuracy out of this depth estimation. And the depth map is shown in this slide, as a in the bottom, that the color shows a different distance. So in this depth map, this the yellow color is farther the object, rather than the blue color is quite near object. And out of that the depth map, we can make a the errors of each the technique, that when the cars are parked in a stationary mode, and in the daytime or in the night, the errors are different. So the range is from 40 meter to the 70 meter in this test. And then well, actually we need more data, but anyway, it's done in a couple of days using using a car of a different other person. So we could not use this for a month. So we have a very limited data, but still we could make the errors. We could make the errors out of it. And out of the 50 meter, in general, we could achieve about 1 meter of an error, and then which is okay for most of the applications. But if it's a 20 meter or 10 meter, then the error should be much smaller than this, like a 0.2 meter or so. So well, it's achievable, but still it needs more work. So the advantage of this technique is to acquire the simultaneous imaging and ranging, and then it's quite cost effective. We are shooting it around $50 per piece, and compact size, it's about a few centimeter in the whole size, and then precise dimension control due to microelectronic fabrication, and then high stability because there is no mechanically moving parts in the assembly, and then reduced optical aberration. In the process of the assembly, and then autonomous cars or robots or drones, can use this kind of technique, and then there is no interference between sensors. But the problem with this one is that it's vulnerable to bad weather, and the accuracy is not, as good as a LiDAR. And so the bad weather, like raining or snowing, then the camera may not detect the whole picture, or accurate picture. So because this technique depends on the quality of the pictures from the camera. Okay, well, third example, I think. Okay, I'll finish it in 10 minutes. Is it okay?
Yes, please.
Okay, thank you. A third example and the fourth example is on the biomedical applications. And this one is a analysis of fluidic bead cube embedded portable CMOS chip for immunoreaction monitoring. So this is on the immunoreaction monitoring, basically cancer cells, and so this is good for point of care biochip, and then it can be portable and provides high resolution. And the advantage of this one is very minimize the sample consumption, and it can be disposable because it's from the again a solid state technology. Well, the system, this device consists of 3 layers, like a the CMOS sensor, which is a temperature sensor, and ion sensitive FET, and then the fluidic cube, which is the bead filling and immunoreaction, and then antibody immobilization using bead flow, and then the assembly of these 3 layers. And this slide shows the fabrication sequence. Well, the one thing I want to point out here is that you can make it disposable. This the blue part is a called a PDMS. So it's a polymer, and basically you can pour it and then cure it, and then it's patentable. So you can make a the channels, which is clear in this slide, and basically you can make a master out of a silicon or metals, and then you can pour the PDMS, which is polymer, and then you can make a the replica of that the master part, and then you can easily bond it, or you can easily take it out. So out of the fabrication, this slide shows a cross section of those devices, as in the ICs, so that you can see all those different types of layers there, and the holes, and this the chamber, and the filter and inlet, So it's well fabricated actually. And the size of this is basically tens of microns. The diameter of our hair is roughly 100 micron, 50 to 100 microns. So it's a little bit smaller than our hair. And in this fluidic bead cage, you can find the pillars, which is a rectangle in this slide, in this diagram. And then you can find the inlets and outlets, of those specimens. And then the specimen flows from the inlet to the outlet, by the pressure from the inlets. And this slide shows the cross section of the pillar, so that we are talking about 30 micron the width with the 5 micron space. And so there are a bunch of arrays of these. And then basically on the bead, you make the streptavidin or the AFP. The AFP is the cancer index, and then kind of other types of bio samples, and then if they so there's an antigen and the antibody in the system, so that if you make a mixture of those, or if the correct antigen and antibodies are the mixed, then it'll make a kind of chemical reaction, and then that is detected by the ion sensitive FE. So here we can talk about the 3 nanogram per milliliter of the detection limit. So it's very small, and then the total the detection time is quite small, but before then you need some kind of the process for the concentration, and then the PCR, and then some kind of flows to fill in and take it out before and after the detector. Okay, so basically the total system size is 21 millimeter cube, and then power dissipation is 5 milliwatt. It's a very low power, small area, small volume device. The last one is not my work, but it's from the Caltech in the USA. But since I'm supposed to talk about this COVID, so and I don't work on COVID, in terms of sensors, nowadays. So I just got this the example, from others. And basically, this is from the Professor Cao. And then you need either blood or saliva of a small volume, and then you can detect, the COVID-19 infection. Basically, it uses a graphene with the patterns, on the right side, and it has a, as in the bottom, it has, that the PCB with a RF transmission function, so that you can communicate with your cell phone. And on the diagram, at the bottom, you can see the array of these devices with the finger of the human with this device. So the size of this device is in the centimeter, and a few centimeter in each side, even to 10 centimeter. And then it uses 4 different types of antibodies or specimens. Okay, so IgG, IgM, and then the CLP, and then nucleocapsid, NP, which is the complex of the generic material of COVID-19. Okay, so and this is the readout, the scheme of this of the signal from this WE walking electronics. Okay. So there are 4 different types of specimen sensors, and then so and as you see, the circuit is rather simple, here. with the analog type circuits, and then AD converter, and then again the communication scheme. At the bottom, you can see the response of this sensor. That MP is for the COVID-19 again. So you can see the selectivity of this in the diagram 1, selectivity of this device, that the blue line is for MP, which is quite differentiated from other signals. So in the y-axis is in the current. So you need to make a big current out of this sensing scheme. So for the again other 3 types of specimen generate less than 1 microampere, rather the MP generates over 2 micron amperes. Okay. And then this slide shows the response or performance or sensitivity of this device with the X of the specimen, and then Y as a output current. So this is quite linear response, and then you can see the rather sensitive the device. And this is quite interesting to see that from the top, if you there are 4 different islands in this graphene sensor, and if you don't get any the signal out of 4 electrodes, then you are healthy. And if you have a viral antigen, which is MP here, plus, then you are infected. But there are 3 types of infection that with the signals from IgM, IgG, CLP, then you are either no symptom but infected, or you are also there's some different types of the infection here. And then you can also show that if you do not have any the signal from the viral antigen, but from the IgM, IgG, CLP, then you are either recently recovered or long-term recovered. So you can show many different types of a symptom of a patient. Okay, this is the last slide. Well, basically, I talked about the some of the examples with the with the silicon technology or polymer technology, but these days people are talking about the module of a sensor or MEMS technology, meaning that it's not only the sensor, but you need a kind of some functions like a the intelligence. So data storage, for the IoT, and then communication, like in the IoT, and then sometimes because of the massive distributed network, then you need the self-diagnosis or make small decision on the node, so that with the far distance communication, you don't want to make a burden to the host computer. And for the fabrication, again on the bottom, you need a nanotechnology and semiconductor technology, as well as the some specific dedicated MEMS technologies. So it's a combined effort with the MEMS people and the packaging people and the materials, and then the circuits and the some of the communication people, and as well. And then you saw the some of the collaboration with even the computer vision or software type people. So it's in the domain of the AI nowadays, with the some. Okay, thank you very much.
Thank you very much, Professor Kukjin, for the great talk on integrated sensors in the age of COVID-19 opportunity and challenges. So we have listened about the MEMS technology and then some applications, and also MEMS applied in COVID-19. So now it's time for Q&A sessions. I would like to read. Okay, there is a questions from
Yes.
Dr. Adila. In recent years, there is a trend toward AI on edge, where AI models are deployed or even trained on edge devices like IoT devices. What are the possibilities for advances in MEMS technology to influence these trends?
Yes. Yeah. Well, you got point. You know, actually these days sensors quite prevailing, and Korean government, you know, is carrying out a national level research, you know, big ones nowadays until next year for 6-year program, and you know, a couple of ministry are thinking of the continuation of that effort, you know, like a semiconductor, you know, development in Korea. So it's coming, and you know, many actually the CEOs, you know, contact me, you know, for possibility, you know, of this technology. Well, if I have the same question in the late 1990 or early 2000 or even up to the 2010, I cannot say yes, you should do it. But nowadays, I recommend them to do it because the for the IoT especially, you know, that needs a lot of different types of sensors, you know, in each node. And for the fourth, you know, the industrial age, the key items are communication and the sensors, basically. So whatever you do, I think you'll be connected to the sensors in some forms. So well, it may not be, you know, your domain, but still you need to collaborate with the sensor people, you know, because that's the only interface with the nature and human body, and you know, and any object. So nowadays, yes, the um, the sensors are quite necessary, you know, for most of it.
Okay, thank you. So I will read questions from Q&A box. Is it possible? How is the possibility of using MEMS on defense or military weapon systems? And also, how to design data link interoperability with different platforms, such as East and Western data communication technologies, and what are the requirements that are required?
Okay, for the first question was on the defense system.
Yes.
I worked on missiles. Yeah, and because missile requires, you know, IMU, so-called inertial measurement unit, that combines of that's a combination of accelerometer and gyros, you know, detecting the acceleration and the rotations, and with that, with those sensors, you know, in 3 axis, you can find the location of the missile. Okay, how far it flies out, you know, from the origin. So IMU, you know, is essential there. And even when I was teaching in the 80s in the US, there was a white paper on the embedded sensors on the soldiers' the head fiber. Okay, for chemical, you know, the war, how to detect those toxic gases, how to detect, you know, all the other environment in the distributed, you know, the environment. So each soldier is a node in the distributed network.
Right.
And then you know, well, so missile and those things, and still, you know, continuing effort on that one. And then what else? Okay, so what was the second question?
Second question is how to design data link interoperability with different platforms, such as Western and Eastern data communication technologies? And what are the requirements that are required? What are the requirements? How to design data link interoperability with the different platforms?
Is it related to MEMS or to communication?
Mr. Pancha, yes, yeah, maybe related to data communications, I think.
Yeah, I guess so.
Okay, so Professor, I would like to ask you questions. Is a COVID-19 changing the MEMS market dynamics? What do you think?
Okay, well, you know, from the year 2000, people have worked on the biomedical system like a Lebanon chip. And Lebanon chip, you know, is a quite similar application to the COVID-19. Because if you just drop a very small specimen, you know, there, then yes, you can detect the, you know, like a Caltech paper, you can detect if you know, the person is infected. Or in the pharmaceutical companies, you need, for developing a new drug, you need you know, the combination of many different types of materials or in different techniques. And for that one, you know, you gotta use a very expensive the samples. And if you can minimize those uses of those samples, then you can make a, you know, more research out of a the rather confined the limited amount of the samples. So that'll reduce the development, you know, the burden. So that's you know, the advantage of MEMS. And then for COVID-19, yes, well, you know, for a like a vaccine, you know, or the any drugs associated with that, yes, that helps, but not much, frankly speaking. Okay, and then for the working environment or those things, I don't think it's related to, you know, the MEMS basically. So you know, compared to the communication or other type of technology, I don't think you know, the sensor or MEMS technology will be, you know, pretty much affected by this current environment.
Okay. Okay, Professor. Thank you very much. I think time is already over, more than 12.
Okay.
Yeah. Thank you very much. And okay,
Thank you
I
very
will
much.
give time to Dr. Adila. Thank you. Thank you, Professor Kukjin. Please
Okay,
give
thank you
applause
very
to
much.
Professor Kukjin. Thank you.
Thank you very much. Thank you very much, Professor Kukjin, for the inspiring talk. As you said, sensors are everywhere, right? Okay. Right. So everybody, right now we here in Jakarta. It's past 12 p.m. So actually, it's lunchtime. So we will have a break for lunch break. We'll start again at 1 p.m. For the next plenary speech from Professor Akinori Nishihara. I hope, you know, you may go for getting your lunch or, you know, taking a break, but but I hope everyone returns for the next plenary speech, which will be also as inspiring as the previous ones. So I'll see you guys in I guess roughly in 45 minutes or so, and we'll be back.
Okay. Thank you.
Okay, everybody, welcome back to ICACSIS 2020 and IWBIS 2020. I hope everyone enjoys the break. After the break now, we move on for the third plenary speech. And before I introduce the plenary speaker and the moderator, let me just mention a few things about the keynote speeches that will be delivered this late afternoon and evening. So first, for ICACSIS 2020, we have 4 keynote speakers. They are Professor Yves Lepage, which will be who will give the keynote speech on 2:30 at 2:30 p.m. later. He is a professor at Waseda University, followed by Dr. Hendrik Skibe from Riken. And then at 4:30 p.m. we have Professor Lance Fung from Murdoch University, and later this evening at 6:30 p.m. we have Professor Vishnu Jatmiko. Before we end up with the closing ceremony of the conference. Meanwhile, for IWBIS, we also have 4 keynote speakers. At 2:30 we will have Dr. Hamam Riza, the chairman of BPPT, and then at 3:30 we have Professor Zainal Arifin Hasibuan, chairman of Apticom, and then at 4:30 we have Vice Admiral Dr. Amarullah Octavian, and in the evening at 6:30 we will have Engineer Beno Pradexo from Solo C247. So that's the announcement. I hope everyone stays with us until the end. And now let's move on to the third plenary speech. For the third plenary speech, we are honored to have in our presence Professor Akinori Nishihara. He is the current director of IEEE Region 10, and the speech will be moderated by Dr. Kurnianingsih, Vice Chair of IEEE Indonesia Section. Dr. Professor Nishihara and Dr. Kurnianingsih, the time is yours.
Thank you very much, Dr. Adila. Hello, everyone. I'm Kurnianingsih, the Vice Chair of IEEE Indonesia Sections. Thank you very much for joining us today. I would like to moderate the third plenary talk delivered by Professor Akinori Nishihara, entitled IEEE and Super Smart Society. First, I would like to introduce Professor Akinori. Professor Akinori Nishihara was the professor at the Department of Human System Science at Tokyo Institute of Technology, Japan, from April 2011 until March 2016. Currently, he is designated professor at the Human Assets Promotion Program for Innovative Education and Research at the Tokyo Institute of Technology, Japan, since April 2017. And currently, he also serves as an executive producer at Tokyo Tech Academy of Super Smart Society, Tokyo, Japan, since March 2020. He has several professional activities and IEEE activities. Currently, he serves as the Region 10 Director of IEEE, and also he served as the ICE Auditor. He obtained a bachelor degree in physical electronics in 1973 from Tokyo Institute of Technology, Japan. He obtained a master's degree in electronics in 1975 from Tokyo Institute of Technology, Japan. And he obtained Doctor of Engineering degree in electronics in 1978 from Tokyo Institute of Technology, Japan. He received many awards. Some of them in 2017, he received the Excellent Educational Practices Award. In 2016, he received commendations for science and technology by the Minister of Education, Culture, Sports, Science, and Technology, Japan. In 2015, he received IEEE Region 10 Outstanding Volunteer Award. In 2014, he received the Best Engineering Teacher Award from Tokyo Institute of Technology. During these sessions, participants are welcome to have an opportunity to interact with the speaker through Q&A box. Now, we start our plenary talk by Professor Akinori Nishihara. Professor Akinori, time is yours.
Thank you very much. Thank you very much for kind introduction. Today, I will talk about a little about IWBIS and then about Super Smart Society, where I work as Chief Operation Officer. Excuse me. Yeah, this is probably not necessary. Dr. Nia already introduced me, but I'm now, I retired from Tokyo Institute of Technology 4 years ago. So and then I was rehired by the same university. So since my student days, I already commuting Tokyo Institute of Technology Okayama campus for more than 50 years. Okay. And I'm now serving as IEEE Region 10 Director. And as you know, IEEE is a big organization. Actually, this is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. It has more than 420,000 members in the world. In Asia and Pacific, we have 130,000 members, about more than 30%. And we have 46 technical societies and councils in various fields like Computer Society, Signal Processing Society, Communication Society, and so on. And we cover more than 160 countries. In terms of technical breadth, we hold almost 2,000 annual conferences every year. And the number of technical documents is over 5 million. We have IEEE Explore, which is called Digital Library. And we have top-sided periodicals. We have more than 200 transactions, magazines, and so on. IEEE has 10 regions in the world, so we divide geographically in 10 regions. Regions 1 to 6 are in the US, 7 is Canada, region 8 is Europe, Middle East, and Africa, region 9 is Latin America, and region 10 is Asia and Pacific. As you see, we are the biggest region in the world, and it has 32% of total membership and still growing. The figure in the last is the difference from previous year. So you see in many parts they are negative, but we are still increasing. And I would like to stress that Indonesia is contributing a lot. Yeah, we have big countries like China or India, and also Indonesia here. well, in total population, Indonesia is the world's fourth largest country. So I hope that IEEE membership in Indonesia will still grow. Now you have more than 2,000 members. IEEE's mission is here to foster technological innovation and excellence for the benefit of humanity. And IEEE's vision is here. Okay, so we are dealing with technology. So we advance and innovate technology for the benefit of humanity. But you know, human beings live in a society, so we are contributing to society. And the current society is changing. You know, if you compare society in the old times, our societies are very different. And so we use the term super smart society. Okay, probably you know industrial revolution in the 18th, 19th century. But in the late 20th century, we have a digital revolution or IT revolution, and it was called Industry 3.0. And recently, well, especially it started in Germany, but they call our current situation as Industry 4.0. It is IoT revolution. And now it is 2020, so we are around here. Well, Tokyo Olympics and Paralympics were expected to be held in Tokyo this year, but because of COVID-19, it is postponed to next year. But still, they will be called Tokyo Olympic 2020, not 21, and Tokyo Paralympic 2020. And we are now here, and autonomous driving cars are already running from in some places, and 5G communication system was launched early this year. Still, services not yet fully implemented. Well, in some places it was implemented, but it is still growing. And well, manufacturing is very advanced, and AI and robotics, or this is maglev cars, maglev train. So these are actually coming, but we hope we have next revolution. Well, Japanese government says that this is Society 5.0. This is CPS revolution. CPS stands for Cyber and Physical Spaces. So we will have super smart society in the near future. So we have to create such society, and also we have to educate new generation people to enhance a super smart society, so that everybody will become happy with those technology and environment. According to Japanese government, well, Society 1.0 is like this, a hunter-gatherer society. Society 2.0 is agrarian society. So human being started to cultivate rice and other plants. And society 3.0 is industrial society by the industrial revolution. So started from steam engine and then electric power and so on. And society 4.0 is information society. So we can use computers, smartphones, and so on, tablets, and we are connected. And following to society 4.0, we are expecting to have the next society, society 5.0. So smart society, super smart society include many aspects, but for example, this is smart agriculture, so multiple tractors are autonomously working. So even old people can control those tractors. And smart mobility, this is the smartphone app to see where the bus is and how many minutes you have to wait for the next bus. Of course, buses are autonomous driving. And smart sky, well, already packets are delivered by drones. And in some cases, multiple drones work by cooperating each other. And even in the ocean, ships or even submarine can work to investigate natural resources in the water or something like that. So for super smart society, we have to educate younger people. So for those young people, they need some skills, but it should be including cyber space technology plus physical space technology, and probably multiplied by quantum science. For example, usually we sense some data by the sensors, and the data is transferred to the computer by IoT or 5G network. And by artificial intelligence, the data is processed and analyzed, and then it fed back through IoT or 5G. So, for example, robots are controlled to work appropriately. But in the near future, we will use quantum sensors for more precise measurements. And also we may use quantum computers in addition to supercomputers. Well, of course, we can use supercomputers now, but there are some problems which is difficult to solve even with the top speed supercomputers. So quantum computers and supercomputers should be used together depending on the problem types. And so the result is used for our city or society. So for the human resources, this is human, but as you see, this is like robots or real human. But in the heart, we have basic of quantum science. So people should have core skills rooted in quantum science and artificial intelligence. And they have to do some original research spanning the domains of cyber and physical spaces. And they will be able to have a big picture from quantum science to super smart society. And they innovate interdisciplinary research to create a super smart society. And we hope they have leadership in academia, government, and industry. In smart agriculture, smart city, smart ocean, smart manufacturing, smart mobility, smart energy, smart sky, probably some more. But these are what we are thinking of. Why Tokyo Tech started this program, Tokyo Tech Academy for Super Smart Society? Because we have world leading professors like in various fields. Professor Nishimori is famous in quantum computing, and Professor Fujita is in systems and control, cooperative robot control, and Professor Takayasu is famous on big data analysis. We also have a Super Smart Society Promotion Consortium. It was founded in October 2018. And more than 30 partners we have. So not only Tokyo Tech, but those consortium members from industry and government institutions are cooperating with us. And also we have sister society for leadership education. And also Tokyo Tech X is a MOOC platform, massive open online course platform using edX, developed by MIT and Harvard. So based on these, we established WISE program. WISE stands for WISE. The term WISE was made by our Ministry of Education. It stands for World-Class Innovative and Smart Education. So they called for programs from all the universities in Japan, and we proposed this Super Smart Society program, and it was adopted last year. So we offer integrated education of physical technology and cyber technology, and also quantum technology from various schools. And we have open education like this Tokyo Tech X, and also open innovation through this IIS Promotion Consortium. And we also educate our students for global leadership education together with this total. Okay, so this consortium was made in October 2018, as I told you. So we held a ceremony of foundation, and in November and December in 2018, we held interdisciplinary matching workshop to build collaborative research teams covering academia, industry, and government. And last year in September, our WISE program for Super Smart Society was accepted by MEXT, Ministry of Education, Education, Science, Technology, and Sports, and something. Sorry, I forgot. So this is a 7-year program, but since we have consortium, IWBIS consortium, we hope will run the program after finishing the financial support from ministry. So this April, we officially started Tokyo Tech Academy for IWBIS. In the beginning, there were 61 professors and 40 advisors from the world. And but now the number is increasing. So yeah, this is IWBIS Promotion Consortium, and we have a WISE program, Tokyo Tech Academy for Super Smart Society. So they are collaborating, and we have participating companies and organizations. So they have also young engineers. So we collaborate with those people. And our research result can be utilized in those parts. And also they offer some R&D results to our consortium. Human resources are also related. And those people join us as part-time lecturers. And young people join our program as PhD students or master students while working in their companies. And our students go to those institutions as interns, or after graduation, they may join those institutions for their jobs. And so this is our university, Tokyo Institute of Technology. So of course, those people, professors and coordinators cooperate with consortium, and we have joint research, and professors teach our students. And so this is rather complicated structure. And for the the advancement of research activities, we built education and research fields in our campus, so that we can promote collaborative research. So, for example, for smart mobility, we have autonomous driving car, and it can run inside our Okama campus, and students can join, and company people can join to have some collaborative research. And also we have other education and research field for quantum science, smart energy, and so on. Okay, so this is, oh, can I run the, oh yeah, no. Actually, this is video, but it doesn't work. Okay, then I will skip. But this is the autonomous car. It has LiDAR and 5G antenna and so on. So it can run inside our Okayama campus. Oh, it works. Can you hear the sound?
Yes, we can hear.
Okay. Okay, so these are our program members, 71 faculty members from 7 schools and institutes, and also Institute for Liberal Arts. Okay, so many people are joining in our program. And also we have advisors from outside. We have 4 special advisors and international advisors, 17, or actually we have one more, and 14 private industry and government and research institutes. And this is one of the course, or actually this lecturer, he's from NEC, and he introduced his research results to our students. And well, even though they speak in Japanese language, we will add English subtitle for international students. And this is on-demand courses, but they can students can discuss online after watching the video, a lecture video. So online courses are very effectively used. This person is from KDDI. Okay. So we have also intensive exercises for mainly doctoral students to plan new research work based on group work in other fields. So we encourage our students to have a wider view of their fields. So they enjoy this autonomous driving cars. This is quantum sensors and AI. In this case, this was online course, so not very interesting. This is quantum computing and smart robotics. So students enjoy these various fields. So even other fields research or experience is very much encouraged. And so we have open platform, and yeah, I will skip this AI and so on. Okay, so this is the end. So, but for example, one PhD student in civil engineering, he is interested in concrete structures like bridges, and buildings. But from this program, he is now interested in quantum sensors to measure the concrete inside of concrete. He can measure precise electrical current by using a quantum sensor. So this kind of research is very much encouraged. So I hope we can create a very nice next generation researchers, and also we will be happy to have students from Indonesia. Thank you very much.
Okay, thank you very much, Professor Akinori, for the great talk on super smart society. Now it's time for Q&A sessions. Okay, we received so many questions.
Thank you.
Okay, I will select several of them. Okay, I will read the questions from Professor Lens Fang. Thank you, Professor Akinori, and we all look forward to the next generations of development in human society. However, the super smart society will depend on two main infrastructures: availability of electricity and communications through internet. However, in terms of nature disruptions, these two can be guaranteed. How can the super smart society be prepared against such disruption naturally and or man-made interference? This is from Professor Langs.
Okay, thank you very much for your question. Yes, for super smart society, we need super smart energy. So yeah, we have to keep our environment. So energy generation is very important aspect, and also we need high efficiency of utilization of energy. So in the beginning, we may need much energy for communication or for computation, but we need to solve those problems to be more efficient, more energy efficient in computing, communicating, and controlling various things. Well, it may not be so easy, but we have to go in that direction to save our Earth and save us as human.
Yes, okay, thank you. Okay, another question is from Dr. Adila Krishnadi. In your description of super smart society, it appears that there is a strong focus on talent development in science, technology, engineering, and math, STEM.
Yes.
What about fields such as social sciences and humanities? How does super smart society accommodate these non-STEM fields into the framework? Are they also receiving attention in the context of multidisciplinary approach of super smart society?
Yes, of course. Well, our university, Tokyo Institute of Technology, is focusing on science and technology, but we strongly think that humanity is very important. So that we established Institute for Liberal Arts. It was only how old are they? 4 years ago, and we have some members from this Institute of Liberal Arts to help us and help our students. So students not only focus on their technical research, but also they are required to have liberal arts subjects and also some discussions among students and so on.
Yes.
Thank you for your question.
Okay. So another question is from Mr. Hisam Ataya. It is about aging populations. As we know that in Japan, increasing aging populations, and how this Japanese society disseminate the utilizations of technology for elderly people and those who stay in rural areas. Does a WISE program covers education for the utilizations of technology in rural areas? And also how is the Japan government accommodate these aging populations in the development of super smart society?
Oh, yes. Well, aging society is one of the biggest issues in Japan. We are running on the top of aging.
Yes.
So we are very much aging. But so one is to have younger generation. So we would like to encourage younger people to have more children. But this is not so easy. But I think we have to change the society so that young people can easily grow their children. That is one thing. But even though we do such movement, well, you know, some young people would like to live alone. And yeah, we cannot force them to get married or to have children. So aging society is coming, really. And but luckily Japan is a small country, not like Indonesia. So even rural areas is not very far compared to Indonesia. Indonesia is very, very wide. So in our case, it is relatively easy compared to your country to have better communication, better transformation, and better education for everybody, even in rural areas. So I hope we can solve this this problem.
Yeah. So continue in that question. I would like to ask: is there any plan from Japan government to prepare like certain area, like in Europe, for aging population, but this certain area equipped by many sensors, high tech technology? Maybe it is one of the way to accommodate aging populations.
Oh yes, well, I'm not sure if government is doing so, but yeah, there are several super smart cities, and some are planned by local governments, and some are planned by private companies. But we have some smart cities where even aged people can live rather easily. Well, we shall see how they can solve our problems.
Okay.
But we are glad to collaborate with those people.
Yes. There is a question from Mr. Agung. How is the implementations of the super smart society in the military field of building constructions faced with the development of cyberspace and computer technology and automations for defense and security that are beneficial to the humanity?
Well, yeah, I'm not so familiar with military technology. So I'm sorry, but I cannot answer this question.
Okay.
And but yeah, for you know, our military is called self-defense force. So it is not officially a military, especially for defense. But yeah, in some parts, technologies are very important in military usage. But sorry, I'm not so familiar with military usage.
Professor, in this current situations, COVID-19 pandemic, does these situations influence the development of super smart society in Japan?
Yes, yes. Everybody is influenced by COVID-19. From early April, we had a state of emergency by the Japanese government, by Prime Minister Abe. But the situation now may be worse than during that time. But gradually, we know more about this new virus, COVID. So we will be accustomed and we can live together with virus. Yeah, like other viruses. Yeah, we have flu. We have many other viruses, but
influenza in Japan is very worse in winter. Yeah, I see. Okay. So, Dr. Adila, do I still have a time? Oh, so many questions because your topic is interesting. Questions increasing.
I think we still have time. I think we still have time.
Oh, we still have time. Okay, maybe I will read one more question. Say maybe one or two.
One or two is.
Okay.
Okay. Thank you.
So another question is from Mr. Randy Ananta. How do you see the relationship between technology and human? Is a human engineered the technology or technology influenced the human society or reciprocally mutual relationships? And his second question, besides information society, how do you see other society models such as network society that all entities, human and non-human, are intensively interrelated? What do you think?
Well, technology, yeah, as IEEE's mission says, technology is for the benefit of humanity. So human first. And technology should be utilized for the human. So human society is what we really seek for. And what is the next question?
Next
other
question.
Society models?
Yes, other society such as network society. Yeah.
Network society. Well, I really don't understand what network society means,
network
but
society.
well, society is actually the networking of people.
Yes, correct.
So yeah, network is important, of course. So like this time we have network of humans in this ICACSIS and IWBIS. So we communicate and exchange our ideas to have better ideas. So networking is always very important.
Yes, correct. I agree with you. So many questions. Okay, so this questions from Mr. Alex. According to your perspective, will Society 5.0 be the initial stage of super smart society? And is there a top level for this term of super smart society?
Yes, yes. Society 5.0 is the initial state of super smart society, and we don't know how far we can go to super smart society at this moment. Probably we will have very different super smart society. We cannot imagine at this moment, but this is our dream.
Yes, correct. I think it's enough, Dr. Adila, or do you want to have another live questions?
Let me check.
Other questions looks similar and already answered by Prof. Akinori.
Yes. Yeah, I think we could have. Okay. Yeah, I think most of those questions are already answered. Yeah. Sorry about that.
Yes.
Thank you.
Okay. Yes.
Yeah,
So I
thank
think
you very much.
yeah, I think we are good. Yeah.
Yes. Okay. If there is no questions, I think already answer almost 28 questions because look at similars.
Thank you very much for many questions.
Yes, thank you very much. Okay, Dr. Adila, I think also time is almost up now.
Okay.
Okay, thank you very much, Professor Akinori Nishihara.
Thank
Give
you.
applause to Professor Akinori.
Thank you.
Thank you.
Very much.
Okay.
It's my honor to be here.
Yeah. So we return the time to Dr. Adila.
Yes, thank you. All right. So once again, thank you, Professor Nishihara, for the talk. It is very interesting and timely because of the advances of technology together with the humanity. So we want, as you said, technologies to benefit all humanities. All right. So right now we will have a break. We will start again at 2:30 p.m. But before that, the organizers, do we have information for the next sessions? Mas Hamid?
Mas Dr. Adila, maybe please explain to the audience. We will split become two session, and which one can?
Yes. Yeah, I think the organizers have a slide to show. Hold on a second. Right. Yes. Okay. Great. Thank you very much. So this is the information for the next sessions. We will start at 2:30. I apologize that the schedule does not appear here, but let me just mention. So for IWBIS, we have 4 keynote speakers. We will start at 2:30 with Dr. Hamam Riza, I suppose, right? With Dr. Hamam Riza. And for IWBIS participants in particular, please join the URL there. We will display this for the next couple of minutes, I think. And then for ICACSIS participants, we will start with Professor Yves Lepage from Waseda University at 2:30 p.m. And the URL to join for the Zoom is also given there. So please stay or please move to these rooms and I'll just make sure later, a little bit, a few minutes. I'll make sure that the rooms are open already.
Dr. Adila, maybe you or Mas Hamid can write this URL in the chat box.
Okay, so Mas Hamid, could you please
for the participant to join?
Yeah, could you please write them down in the chat box? Yeah, both IWBIS and ICACSIS. Professor Lansfung, the IEEE Day link will be provided separately. I think Dr. Nia will.
Yeah, I already sent email to Professor Lance. Yeah. For the IEEE Day link, and also Professor Akinori Nishihara. We will have a IEEE Day celebrations at the same time with the parallel this conference.
Yes.
3 parallel events. Okay.
All right. So thank you, Dr. Nia. And with that, let's have a nice break. We deserve a break, right? So anyway, let's have a nice break, and we see everybody hopefully at 2:30. Mas Samir, just make the slideshow for the next couple of minutes so that the participants can see that. Thank you very much. See you in a